Hello, welcome to another stream. How about that? How about that? Okay, sorry. Hello, Mr. Botcut, Sodium TOS, Nitrix Life, Megalazos DS, Aiguduk, Yatanasov, Her Hotson Plots, Her Hotson Blots, F Mega, this Nur, hello, hello, I hope I didn't miss anyone, Ikura Ball, hello, hello, welcome, welcome, welcome. So today is Wednesday, say the line chat, it's Wednesday. Anyway, so today is Wednesday, and that means today, according to the schedule, we're gonna be developing, we're gonna continue developing our virtual machine. And we reached the stage of the development of this virtual machine where we're trying to take the bytecode of the virtual machine and compile it to a big boy native real code. That's right. So what we're doing, we're trying to generate x86-64 assembly out of it, and our goal is to make the generated assembly a self-contained program that you can then compile and run it. So effectively, we may have like a simple proper language that, you know, translates into assembly, and then you can compile it to a program. So yeah, technically I think this could be like Basm could be my first proper language that actually works. I had a lot of attempts at developing different languages. Majority of them were just interpreted languages, and a couple of attempts at compiled languages. This one could be my first attempt, like that actually works. I mean, yeah. So before that, my attempts were kind of like toy attempts. They don't count. But yeah, F Mega, hello, Shiggy Man, hello, hello, and no IO before bed, hello, hello. So, yesu, kawaii desu. Alright, let's go to the virtual machine. So, here it is, git branch. And a status, let me check the status. Check it out, check out the master, and let's fetch the latest stuff. Are we gonna first try it? We fetched first try, that's right, first try fetch. Very impressive, I know. Origin list. Well, I mean, I couldn't merge first try, for example. You see, it's hard. Using Git is hard. Sometimes you can first try fetch it, but sometimes you cannot even first try merge it. So yeah, so you need a second try. Alright, so let me actually remove this branch x86-64, and I think that's it. I think I can just try to build everything. So I have two separate builds, just a regular build that builds the tool set and compiles the examples into the bytecode, and I also have an experimental build that also, on top of doing the same thing, builds some of the examples into assembly and then links them into actual executables. So we don't have all of the examples working, but one of the most important examples actually works, which is a Fibonacci sequence generator. So the original Basm program for Fibonacci sequence generator looked like this, right? So, and we turn it into assembly, x86-64 assembly. So this assembly was generated from the bytecode. It's a little bit verbose, it's bigger than the original program, but this is because we don't optimize, we don't try to, you know, make it concise or fast or anything like that. We just want to make it work, and we want it to be self-contained. And it actually works. The next thing we did, we actually generated an executable, elf executable. You see, so we have an elf executable which is statically compiled and stuff like that. Doesn't depend on anything, and if you run it, it generates Fibonacci sequence. So yeah, that's pretty cool. I'm really proud of this achievement, by the way. I didn't know that I would be managed to do that. Like, I thought it's gonna be a huge pain in the ass, and it turned out to be like easier than I thought. Generate C code and then compile with O3 instant mega performance. What's interesting is that I think at the first stages of Jai development, John Blow did exactly that, I think. So essentially, like, first version of Jai were just preprocessors to C, and in some of his old demos he actually talked about that, and he actually showed that. So yeah, essentially, like, he used C as a cross-platform assembly. which actually makes sense because this assembly, for example, is not cross-platform. But what's interesting is that the reason why I'm not using C, Nim also still does that, yes, Nim also still does that. The reason why I didn't use C is because I wanted to be closer to the actual architecture, because eventually I want to get rid of that third-party dependency, and to get rid of that third-party dependency, I need to know exactly what instructions to generate, like precisely, and that's why I'm using this thing. So eventually, like I essentially developing my own LLVM, as I already said. What's up, Gail? Welcome to the stream. Rotten Chumsy. Hello everyone. Hello everyone who just joined. So yeah, it's kind of interesting. I'm kind of developing my own LLVM. He renamed himself to J Blow on Twitch. Interesting. I think he talked about renaming himself for quite some time already, right? So because I mean, who knows who's naysayer, right? So everyone knows John Blow. So it makes sense like to rename himself, but maybe that's not the reason why he renamed himself. So anyway, yeah, let's continue doing this entire thing. So one of the problem here that I think gonna face is implementing print float. Alright, so if I take a look at some of the examples here, like specifically, again, Fibonacci example, when we're generating the code, we supply implementation for print I64. Printing integer numbers in assembly is actually extremely easy. So as you can see, I just implemented that myself, like there's not that many instructions, you just iterate, divide, and chop off the numbers until you get 0, and that's literally it. So, but another thing that the BM environment is supposed to support is print F64, right? Print F64, and it's kind of like printing floating point numbers is kind of difficult. There's like a lot of research put into printing them precisely, and there's a lot of like scientific papers and shit like that. So usually when people need to print floating point numbers, they just use printf, but I'm trying to make this executable self-contained and not depend on any third-party dependencies. So because of that, I will have to implement printf64 myself somehow. So I think this is going to be the biggest challenge in this entire situation. I think like everything else is super easy except printing floating points. So I don't know, we'll see how it goes. To be fair, I think the simple algorithms are not that hard to implement. It's gonna be pain. Yeah, so the simple algorithms, like, I don't know, like with a fixed precision, they're all well documented. We can just use one of them as a placeholder because these print functions are supposed to be debug functions anyway. Right, so they're not supposed to be like a proper print functions anyway, like they're not on the level of printf. They just take whatever you have on the stack, they consume that from the stack, and they just print it. So can you just call PHP? I can call your mom. Hello, Penguin Ray, welcome to the stream. No, we cannot call PHP, I'm sorry, it has to be self-contained. Alright, so I'm gonna be thinking what I'm gonna, how I'm gonna implement that. So I think I even tried to look it up. Printing floating point numbers. I think it was something like precise printing. And the paper that I remember I saw was dated 1990. So yeah. Oh, also it's behind a paywall or something, so maybe we can actually grab it from here. How to print floating point numbers accurately, not precisely, but rather accurately. So yeah, this one. So it's a rather old paper, and I really like old computer science paper because they are less obscure than the modern ones. We can try to, here's the algorithm, by the way. They actually look into several algorithms. The first one, the simplest one, is called fixed point fraction output, and they even say that that's not really the algorithm they recommend. I think I didn't really read into it, but they just provide it as an example, and they develop more precise and better algorithm in the future. But I like the simplicity of this algorithm. This is the entire algorithm in Algol, right? So we can try to translate it from Algol to, to C or to assembly, right? So preferably to assembly, but we'll see. So, and to be fair, I don't know how to implement that because I don't really understand majority of these letters. But since the code is so concise, we can just, you know, try to crack it together on the stream. What do you guys think? Does it sound interesting? You know, that sound interesting? Implementing floating point printing on the stream and reading scientific papers. Sounds pretty cool. Alright, so let's actually go and do that. Okay, let me go to the generator. Well, I mean, technically you take a higher level language and you translate it to a lower low level language, so it's really the generator. Anyway, whatever. So damn it, stop mocking me. Why did it say fixed point in the headline of the algorithm? I have no idea. Maybe because it's literally fixed point. Oh, is it fixed point in a mathematical sense, like a fixed point function? You know, fixed point function. It's not really a function. It's like a fixed point. Like, you know, in mathematics, maybe this one. So a fixed point of a function is an element of the function domain that is mapped to itself by the function. Yeah. So essentially, a fixed point p for a function f is such a value that f of p equal to p. So that's the fixed point, as far as I know. So, and what's interesting is that there is a like well-known process of finding fixed point. You start with some sort of initial value, and you keep applying a function many times until you find until the value of the function doesn't change anymore. And that's the way to find a fixed point. You can even do that on your calculator. So essentially, just if your calculator has a sine or cosine, you can just put a random number and keep pressing cosine or sine, and your value is going to be approaching to the fixed point. So yeah, maybe it's related somehow to the notion of fixed point in mathematics. Not fixed point in a sense like a fixed precision, but something like this. So yeah. So this algorithm is trying to find a fixed point that can't be reduced anymore. I suppose, yeah, I guess. We're about to find out. All right. So here's the thing. I don't really like generating like fixed implementations like that. Like literally, this is just a text, and I'm printing just a text, and it's so inconvenient. And then I'll have to like write a function, static void gen print f64 like this in a similar style, and it's so inconvenient. I'd rather have a separate file where I have this implementation, and I would just print that file while generating everything. But that will require like reading files and stuff like that. So I'm thinking I'm gonna go the approach I did with Suwon, right? So in Suwon, there is a sprite sheet. Right, there's a sprite sheet that is used for rendering the letters, but it's baked into the executable. Right, it's baked into executable. So what I'm gonna do, I'm gonna bake some of the source code into the executable, and then I'm gonna just print them as the, you know, as the resource. Yak shaving. Yeah, we're doing a little bit of a yak shaving, but I think it's necessary because I want to create myself a comfortable environment where I can code in assembly, because this is not convenient. I want to have like highlighting and stuff like that. I don't want to be worrying about whether I put new line or didn't put new line. I don't want to do any of this shit. Come on. It's 2021. Can I have a comfortable environment to program in, like Visual Studio Code or something like that? Let's actually fire up Visual Studio Code. So where is it? VS, is it? Yeah, VS Code, no sandbox. Yeah, so I wanted something like that, Visual Studio Code. And, well, we need to wait a little bit until it actually loads up and stuff like that, of course. It's a Visual Studio Code. You have to pay for the comfortable environment to program in, right? So, yeah. And there we go. All right. So how do I open shit here? Right. This shit gets me every time. Holy shit! Like, okay. So open folders. Okay, let's try to open folders somewhere. I'm gonna go to programming Zozin BM. Okay, so did it open like a completely new thing here? There we go. Later, alligator. Look at that. Look at that legitness. Okay. So what I'm gonna do? I'm gonna actually open something like print i64 ASM, right? Print i64. Like no, I want to create a new one, and I'm going to copy paste this entire thing there. No, it's not really convenient. I'm sorry, I'm joking. Print i64 ASM. So it's just a little bit more responsive. Emacs in that sense a little bit more responsive, unfortunately. Very sorry. Sorry. Watching Sodin in Visual Studio Code. Visual Studio Code is not really that bad. I mean, it's less responsive on my machine. I don't really have a fast machine, so yeah, I need like a little bit more lightweight editors. Emacs lightweight editor, I know, haha, very funny joke. Very funny, very funny. But it is more lightweight than Visual Studio Code, seriously. It's just like it's factually true. So it is objectively best editor for Haskell at the moment, nothing else comes close. Probably. Funny joke, maybe. And to be fair, like I'm usually programming in Haskell just using two tools, GHCI and Vim. So essentially I just usually do GHCI main.hs, right? Wait a half of an hour because GHCI takes some time to load up. Ivanhoe, hello, welcome to the stream. Hello. Why is it? Okay, and then if I want to edit something, I just start like editor like that, and then I close it. What's interesting is that I can do some stuff here, and then I close it. It automatically reloads things, and yeah, this is how I literally work in like with Haskell. And I don't know, I really like minimalistic development environments. Isn't there an Emacs thing that wraps GHCI? Yeah, but it breaks very often. So the problem with that thing is just it's literally like breaks very often. So I just like to not rely on it. The thing is, it's like I wasn't always like that. You may think that this is because I'm some sort of like a old boomer developer who got used to using only, you know, bare like minimum editors because this is what I had in the past. No, it actually was quite the opposite. When I started programming, there was like a lot of like these rich IDEs. Well, at least Eclipse and Visual Studio were around, and they're pretty heavy IDEs, and I was programming them. But over time, as these IDEs become more and more clunky, more and more annoying, and as I learned a lot of different technologies, and then I had to like marry these technologies together, I realized that to achieve what I'm trying to do, I need to like cut down on the fat in my development environment. So this is something that I came to over the years. It's not like that's something that I got used to. It's actually like happened to me over time. So yeah. I don't know, it's kind of weird. Maybe this is like specifics of what I do. As I mentioned, like I don't stick to a single technology for very long, right? I switch between things, and to be able to effectively switch between things, you need your development environment to be simplistic. Because sometimes you may go into a technology stack that doesn't really have a good development tooling, and what are you gonna do then, right? So, but that's not the truth for majority of people. So I do realize that. So I have like a special case, I think. All right. So let's continue. I'm gonna have a separate file, and I need to turn this file into CRA, which I can then link to my main program, right? Zozin, explain what I'm going to do. excuse me, like I didn't understand the question, I'm sorry. All right, so we could probably use something like XDD, but XDD like doesn't work on all of the platforms. Okay, let me reword that. Like it's not available in the path of all of the platforms, right? So for example, on Windows, it's not available out of the box, right? But it does work on Windows. Like you can find the source code of XDD and compile it on Windows. And the source code is actually quite minimalistic. And yeah, you can even make it a part of your project. So, and what this is essentially what it does. It can take any file and turn it into a C array, right? So this is literally what it does. It takes it and turn it into a C array. It was because you talked, what are you going to do? Oh, I'm sorry, like my brain actually moves very fast. It switches the context all the time, and like in like 10 seconds I might like switch to a completely different context and don't understand what you're talking about. So I really apologize for that. It's just like, I guess this is like a side effect of streaming, right? Because you have to constantly like focus on too many things, and sometimes I just, yeah, I'm sorry. Yeah. So essentially, we could use XDD, but XDD, like, even though it's quite minimalistic, it's still bigger. The source code of it is still bigger than what I need. And to be fair, I can implement such tool myself. And as a matter of fact, I did that multiple times. Right, I did that multiple times. And in Suwon specifically, right, in Suwon specifically, I have this thing. Wait. Oh, it's called PNG2C. It is called the PNG2C. So I cannot just copy paste this entire thing because it needs to not only take the content of the file but also parse the PNG. So and then it uses raw data. So we'll have to implement this thing ourselves. Alright, so let's implement a simple utility called something like file2c. I guess file2c.c. How about that? Sounds cool. And yeah, so let's try to do that. But maybe we don't have to do that. Let me take a look. So what's the license of XDD? XDD source code. I might as well actually just take it until we fake it. So my hexdump facility JW. Permission is granted to distribute XD under X11 MIT, okay, or GPL at the user's choice. Small changes may distribute freely and credit me, make money and share with me, lose money and don't ask me. Nice, that's a good license, I like it. But I'm not sure if I'm gonna make too much money out of that, but maybe I will. So this is the whole source code of XDD. I think we already discussed that at some point, so I'm gonna just take this entire thing. So it's a part of the Vim, and so I don't want to implement this shit myself, that's for sure. Minus 24C, quite cold outside. Yeah, it was a little bit colder recently, like a week ago. In Siberia we had minus 40, and I almost got a frostbite because of that. So it was kind of dangerous. Yeah. Anyways. So let's go. Doesn't it consist of HTML? You mean Frostbite? No, Frostbite is when you get like your skin damaged because of the cold. It has nothing to do with HTML. XDD.c. Oh, you mean XDD.c? Oh shit. Fuck. I see. I guess I'm an idiot. So what I meant here, actually, I meant to click on row. I forgot to click on row. Thank you so much. Yeah. I'm not a very smart person. So here it is. Thank you so much. So VI said blah blah blah. I'm literally like using. Oh, okay. Look at that. XDD is smaller than BM. BM is actually bigger. Like the size of BM is like 1.5 thousands of lines, and the size of XDD is actually like almost 900. So yeah. Our thing is more complex than this one, so it is not a GNU XDD. Is the one that I use a GNU XDD? XXD, I mean. I don't think it's the GNU one. I don't know what is going on here, but there's something really strange going on. There's something really strange going on with this man page. I don't really know what exactly, but... Oh, okay. Huh. No, it's the same, JW, okay. And yeah, this is literally the license, so I think it's the same one. Alright, anyway, so let's compile this thing in build sh. Will probably be a GPL if it was GNU. I think it is... you can use GNU at your choice, actually. So they said that in the license. So what we're doing, can I compile it with my flags? Is it possible? XXD, src, xxdc, and I don't think I want to link it with any libs. I don't think it's required. And let's try to build all of that and see how miserably this shit will fail. It probably will fail with shit ton of warnings because majority of the C developers, they don't give a shit about warnings or anything like that, right? So implicit declaration of function fd open, did you mean f open? Yeah, there we go. fd open. So I suppose there is a flag that discriminates between windows, right? Because this thing compiles on MSVC as far as I know. Microsoft or Win32. Yeah. So yeah, on Windows it actually like defines different things, and on Cygwin, so it tries to be compilable like on as many platforms as possible. So, but fd open, so you need to include stdio for fd open to work, and it's kind of strange that you probably need to like include POSIX-C source. That's probably what you have to do for fd open on Mac. Okay. Interesting. But what do they use on Windows then? Like on Windows, like if it's a Windows. And what is this even file? So this is a main Amiga. This program doesn't work when started from the workbench. This shit works on Amiga? Wait a second. Well, Vim, as far as I can remember, XXD is actually part of Vim, right? And Vim does work on Amiga. Because it was originally like actually developed on Amiga, I think. Or maybe, yeah, so it says it works on Amiga OS. Like, that's actually pretty cool. Does it still work there? I wonder. It's actually quite impressive if it still works there. That's actually pretty cool. But maybe if it doesn't work there anymore, but this could be like leftovers from the times. It was first developed on Amiga, I see. Okay. Okay. Anyway, so I think what I'll have to do, I'll have to probably do something like POSIX-C source. And when I'm building this entire stuff, I'm gonna just do POSIX-C source. Yep. And okay, so conversion to long unsigned int from long int may change the value. Okay, that's very interesting. Is this that big of a deal? Is this that big of a deal? So yeah, as usual, conversions, like nobody cares about conversions. But overall, yeah. But apart from that, it does compile. I was just a little bit like worried about these things. Okay, let's create a separate branch, and on the separate branch I'm gonna do what? So what we're doing, we're refactoring the source code, we making changes to the generator. Let's call it just a bosom to NASM, right? So this is going to be the branch, and this is basically what we're doing here, right? And I also want to git ignore xxd. Tabs and spaces mixed. Who cares? I mean, whatever. Tabs and spaces. All right. So this is going to be the first commit. Add xxd to the source code. What I care about more is about like possible bugs that could be introduced due to careless use of conversion, right? So I want to like actually look into these warnings and see if this doesn't introduce anything dangerous. But anyway. So now, once you have xxd, right, the thing we can do, so we have the original ASM file, right, that we want to basically turn into array. And how I'm going to do that? So in here, I have xxd, and it's going to be src print i64, and I have to provide this flag -i. And I'm going to save all of that to probably src print i64, maybe something like .asm.h, right? .asm.h or maybe .c. It depends, because it doesn't really put any guards there, but who fucking cares? And once you've done that, right? So here is your source code. Kamozu, thank you so much for 9 months of tier 1 subscription. Thank you, and welcome to our hacker club, I suppose. I'm not doing anything like hackerish or anything like that, like or anything infosec related, but I'm just playing with assembly a little bit. We're doing a very interesting thing actually. I don't know if you caught me explaining what exactly we're doing, but essentially we're developing our own small virtual machine, stack-based virtual machine. We already have a simple assembly for that machine. For example, it's still incomplete. You can implement like Fibonacci sequence generator. So this is the simple program for that machine. So we have tooling that takes this assembly and turns it into the bytecode of the machine. So the bytecode of the machine looks like this. So here's that. We have an emulator that can take that bytecode and execute it. So we can take a look at that. So BME example fib, I think like this. Okay, so it just generates like n Fibonacci numbers. Pretty straightforward. But here's the next step. We're trying to write a program that takes the bytecode of that machine and translates it to x86-64 assembly, to a self-contained x86-64 assembly. So if you compile it, you will get a static executable that acts exactly as you would just interpret this thing. And we managed to do that specifically for the Fibonacci example. Our translator doesn't support all of the instructions of the virtual machine, but it supports enough for this example to work. So bosom to NASM, we use NASM to do that, so it's actually pretty straightforward. So what it does, it just iterates through the instructions of the virtual machine, and for each instruction it literally just spits out assembly, right? The result of this translation looks like this. Yeah, there we go. Here's the result. So for each instruction we have like this like block. It's not optimal by any means, but it works. It does exactly what it needs to do, and it's self-contained. So it also like allocates its own memory for the stack. There's some mapping between the address of like x86 address and our instruction address, and so on and so forth. And the resulting executable is this example fib xz. So there you go. It's statically linked. Right, it's very small, relatively small. I don't know how small you can get it, but it's 12 kilobytes, like it's just, you know, assembly. And yeah, we can even do LDD. It's a dynamic executable. And if we try to run it, it does exactly the same thing. it does exactly the same thing as if you try to interpret that program. So we managed to achieve that. So yeah, but as I already said, we don't support all of the instructions yet. So some of them are not implemented, some multiplication, division, some of this stuff, and we're working on that today. .exe, I put .exe to easy, to get ignored easily. MIP64, is it like RISC-V? I never tried MIPS, so I don't know. So yeah, this is basically what we're doing. So the source code of this entire thing is available here. It's not finished by any means, it's just my research project. I'm just like, I never implemented a virtual machine before. So yeah, I'm just playing around with this concept. Do you do JIT compilation already? No, but I just translate bytecodes to assembly. And the reason, by the way, why I'm doing it is I'm trying to figure out exactly what instructions I will need for a single instruction of my virtual machine. And once I figure out all of the instructions that are needed, I can try to make a JIT compiler. I will try to actually get rid of the third-party dependencies on this assembly and generate all of these instructions myself. And once I will be able to do that, I might try to implement ahead of time compiler or just-in-time compiler for this virtual machine. So should be pretty straightforward. You just like allocate a chunk of memory that is executable. You just compile. You instead of like generating text, you are generating like native code into that memory, and then you just jump there. Well, at least this is how I imagine it. I never done that before, but yeah, should be pretty straightforward. So that's what we're doing. This could effectively be a JIT with maybe a few lines of changes, maybe. But since I never actually implemented like JIT or anything like that, like I'm still like learning how to do this kind
The
of thing.
world is in a dark place but studying teaching us about assembly code makes everything okay.
Thank you so much for 5 months of Tier 1 subscription. Thank you, and welcome to our Epic Assembly Club. Thank you. Just dump the ASM into RWX memory and you're done. Yeah, so that's exactly what I'm gonna do. But what's interesting is that like there's probably no cross-platform way of creating RWX memory. Like on Linux, you'll have to use mmap. On Windows, I have no idea how to do this kind of stuff on Windows. On other Unixes, mmap has slightly different signature, right? So you have to probably write some sort of like abstraction. VirtualAlloc and VirtualProtect, I see. But we're actually kind of like far from that yet. So yeah, I haven't figured out everything to make it a JIT yet. So, but I'm working towards that. For sure. Okay, so Debian paste something interesting. Did you make it work on FreeBSD? Holy shit! Okay, it works on FreeBSD. All right, so that's pretty cool. Oh, I mean, come on, that's cheating. That's cheating. But I mean, since it's a part of FreeBSD, maybe it's not that much of a cheating. But yeah. JITs are just objectively worse than AOT unless you're dynamically loading code. True. Yeah. Because a JIT is also difficult to like implement, right? So I don't know the techniques on implementing JITs, but the ones that I heard is that you're trying to identify like hotspots of your program, and you only compile those spots. So that means you will have to implement this machinery that measures how hot a particular spot is. And with AOT, you just don't have to do that. You just grab the whole program and you compile it, and that's it. And you already have like the compiled and optimized program. So yeah. For something like Java, JIT does make a lot of sense because Java relies a lot on dynamic loading. So yeah, but for my thing, I don't think we will need JIT. So AOT would be actually enough at some point. What does the BrainDelph do then? I think it just runs it in a compatibility mode or something. It says that FreeBSD should use the Linux syscall convention. Ah, interesting. Okay. But which one? 64-bit or 32-bit? I think 64-bit, because they have kind of different convention. Anyway, so right now I'm doing like a little bit of a chore of reorganizing the builds and stuff like that. So, right, some of the things that are generated are basically hard-coded, like functions that print numbers. And what I'm trying to do here, I'm trying to actually bake them into the executable as a resource, so I don't have to do this stupid shit with printfs anymore. So, right. So essentially, I just want to be able to modify these kind of things in a proper file, because like editing it like that is a huge pain in the ass. So that's what I'm doing. So I'm using XDD to convert the file into CArray, and I'm going to be merging, linking this CArray with the main program and just, you know, printing it and stuff like that. Alrighty, so let's continue. So it was XDD, so this is what I did here, and then I should be including this stuff somewhere here, maybe. So include print i64asm.h, and instead of doing all of this stupid stuff, print, what I can do is I can just use fwrite. So I print, I think it accepts first the buffer that you want to print, then the size of the single element, and the size of the single element is 1, but I mean, we never know what's going to be changed in the future, so I'm going to do it like that. And then the amount of this element, and the amount of this element is actually well known, and we're printing all of that to the standard output. There we go. So, and we can remove all of this stuff, it's just not needed anymore. Yep, there we go. So that's pretty cool. And now I can have this as a separate file. I can edit it as a separate file, and it gets baked into the executable through this XDD process where we generate like a header. So this is the same thing. So this is this, one more time. These are bytes of this file. There we go. Freshly baked executables. Yes, that's what they are, freshly baked executables. All right. So, but I think it doesn't really, it's not really finished yet. So after we did XXD, this one is difficult. So first I need to compile the XDXD, then I need to generate this entire stuff. So where's my XXD? So, all right, and only then I can compile BASM to NASM. Cool. Nice. So let's try to compile this one more time. Take some time. So these are just warnings from within the XXD. I have nothing to do with them. So also I don't use this thing. I should have been using it. Right. Cool. So that's pretty interesting. Nice. So if I try to, for example, make any changes into that assembly file, right? Into that assembly file, and for example, introduce something that is not compilable, and I will try to rebuild this entire thing. Build x86-64, right? So it should fail. Label alone at line, yeah, there we go. So as you can see, it failed, but it failed in a different place. Cool. So yeah, that's pretty convenient, I think. I think that's pretty convenient. So the reason why I wanted to have it like that is because now I can have print f64 asm, right? And it's going to be a separate file here. i64 is going to be print f64, and we're going to instantly return from that, and there we go. So now we need to learn how to print floating point numbers, because I want the executable to be self-contained. So yeah, it's gonna be fun. But before we jump into that, I think I want to make a cup of tea. While I'm making a cup of tea, does anyone have any questions? Maybe anything? There's some serious coding here. I wouldn't call it serious. It's actually more of like it's as unserious as it can get, to be fair, because I'm not making anything useful per se. So I'm just implementing a virtual machine and just compiling it to assembly. Like, it's just who needs that? I mean, we have shit ton of virtual machines out there that are actually used in production, and a lot of like very smart people put a lot of time into optimizing this virtual machine. Why the fuck we need another one? What am I gonna? I'm coding a virtual machine. That's what I'm doing. So yeah, nothing special. Does anyone have any questions? What are you coding? Because BASM is comprehensive, you think? You think it's comprehensive? I guess it is fun to program in BASM because, like, there is a little bit of a novelty of this machine not having any registers and doing everything through the stack. But it's not that much of a novelty, I don't think so. So, yeah. So you have to, like, mess with the stack a lot. But things like swap and dupe actually make it super interesting, super easy to program in. So, yeah. Okay, so I'm gonna go to the kitchen, just, you know, boil up some water, don't go anywhere, and we're gonna continue programming in assembly. I think BASM has a potential as a novelty VM whenever it gets a proper FFI. I know Jock will try to implement something in it. Okay, so yeah, proper FFI, I think we can do what we can do about it. So proper FFI probably will require a lot of work and a lot of design to get it right. Yeah, because I think getting it right is going to be the most difficult part. Right. All right. I came back. Where's Zojin? He's gone. Zojin is gone. Alright. So, we are about to read some 5-head papers. Are you guys ready? Are you guys ready? Here you go. So this is what we're going to be reading. It's this one. So we need to learn how to print floating point numbers. I never actually implemented it myself. So, and I'm gonna take it as an opportunity to learn how to do this kind of stuff. So I'm gonna get this paper, PDF. So, and let me open it in MuPDF. So, the algorithm that we're gonna try to implement, we're gonna try to implement it in assembly or in C first. I'm not sure, because maybe it's going to be easier to implement it in C to make sure that it works. So MuPDF, I'm using MuPDF, right? So to invert colors, you press I. So yeah. So if you use it, you can use it as well. So it's pretty convenient. I think you can even put that command to the config of MuPDF, so it automatically reverts everything. But I never know what's gonna look good in a dark mode, so I just do it myself every time I open it. Dark paper, yeah. Okay, so here's a procedure for finite precision fixed point. Benny Darshan.
You are using a dark team, so you had to subscribe.
Thank you. Thank you so much for a 7 month of tier 1 subscription. Thank you, thank you, thank you. And welcome to our epic dark theme mode. I'm not that big of a fan of dark theme myself, but I noticed that people subscribe more if I use dark theme everywhere, and that's why I use it everywhere. Thank you so much for the subscription. Thank you so much. All right, let's continue. I want to kind of first implement that in C, just to see if it works or not. Here's my Emacs. So print F, all right, so it's gonna be print F64C std out. So what are we trying to print actually? What are we trying to print? Let's try to print maybe pi, print I64, F64. 3, 14, 15. I don't remember the rest of them, sorry. Yeah, so this is gonna be, let's say, double, right? So this is gonna be the number that we're trying to print. And here is the algorithm. So they have something called k, which is initially equal to 0, right? So it's initially equal to 0, and I have no idea what is k. Right, so let's just bring it. So I'm gonna assume that it's probably a float. So this is what it is. Then we have r. I'm gonna also assume that it's, you know, float, and it's equal to f. And I have no idea what is f. So maybe it is the original number that we're trying to print. I lost everything. I lost my position in the paper. There we go. Maybe that's the number, because I don't see it being mentioned anywhere here. So it's probably, yeah, and we keep modifying this thing, so it makes sense that probably f is the input. Doesn't remember he generates pi digits in a head at one time. Yeah. K looks like a loop index. Okay, so if it's a loop index, it makes sense to make it integer. Thank you. So, and it's gonna be just 0. Cool. So I'm gonna try to assume that x is that. So in that case, I'm gonna put it like that. But I'm not sure if it's that's what it is. Then we have m, right? M is b to the power of minus n and 2. And to be fair, like, I don't know what is n, so maybe we should just read all of that. Maybe we should just read all of that. Let's actually read this entire description of this algorithm. Following Knuth 69, it's not even 69, it's 68. God damn it. All right, we use notation this to mean the greatest integer not greater than x. Seriously? We call it floor. Like, I mean, come on. This is floor. It's not, you know, greatest integer greater than x. I mean, it is technically, but I mean, come on. Cut it off. It's floor. All right, thus 3.5 is equal to 3 and minus 3.5 equal minus 4. Right, so it's a floor. So you round it down. If x is an integer, then x equal x. Similarly, we use the notation ceil to mean the smallest integer not less than x. Okay, so they're explaining the concept of floor and ceil. This is how all this paper is. They have to explain the concept of floor and ceil. Anyway, so I think my water is ready. And yeah, so I'm gonna be back soon. I'm back. Back. How's it going? Welcome, welcome, welcome. How to go and do IRL stuff now? Can't watch the most interesting part. Well, you can always watch in a VOD, so you can be a VOD friend. All right, so so means a ceil. As following note, we use the notation x to mean x mod 1. Okay, so yeah, it's either 0 or 1. The fractional part of x, the fractional part, we use notation this to mean x mod 1 or x. All right, so it's a fractional part of this thing. We always indicate numerical multiplication of a and b explicitly as this xb, because we use simple juxtaposition to indicate the digits in a place value notation. I see. So I think I remember. So basically this indicates not multiplication. So we see you have f minus 1, minus 2, minus 3, and so on and so forth. This is not multiplication. This is like literally where the digits are placed. So that's why they indicate the multiplication explicitly, right, when they mean it. Makes sense. That's actually a pretty good idea. The idea behind the algorithm is very simple. The potential error in a fraction of limited precision may be described as being equal to 1 have the minimal non-zero value of the least significant digits of the fraction. The potential error in a fraction of limited precision may be described as being equal to 1/2 the minimal non-zero value of the least significant digit of the fraction. Okay, so essentially, if you have a fixed precision, so the potential error is half of this value. Right, it's somewhere here. So it kind of makes sense. So like up until this digit, everything was accurate, and then we actually hit this thing, and we don't know whether it was rounded up or not. So the error is somewhere there, so we just assume that it's there. I guess that's what it means. So the time of writing this paper, they had no gain. Yeah, so for those who doesn't know, our virtual machine has a gain instruction for some reason. Yeah, so it stands for greater equal for integers. Right, we have a Jeff instruction, greater equal for floats, and we have a gain instruction, greater equal for integers. Yes, so they didn't have a gain instruction. So we have a lot of great instructions in our virtual machine, believe me. Okay, so the error of fraction of limited precision, okay, so it's somewhere there. The algorithm merely initializes a variable m to this value to represent the precision of the fraction. Okay, so m actually keeps track of that error. So remember how we had m like somewhere here, like in the algorithm, so we assign it to something there. So yeah, it's basically, it tracks of the error, and that's why, yeah. So here's the n. N is the precision, right? So n, how many things we want to actually print, right? So this is the precision. And it's basically, and what is b? b should be some sort of a radix, I think, if I remember correctly. I think it's a radix. Whenever the fraction is multiplied by b, the error m is also multiplied by b. Therefore, m is always has the value against which the residual fraction may be meaningfully compared to decide whether the precision has been exhausted. Okay, that's interesting. Algorithm FP. Finite precision, fixed point, a fraction printout given. All right, b is the base. Oh, okay, that makes sense. So finite precision, fixed point, fraction printout given. N digits, radix b, fraction f, where f is 0 that. Okay, so this is what we have here. So here are like the digits. A radix b, an integer greater than 1. All right. N digit radix b, radix b, an integer greater. I don't understand what's the point of this thing. So this is a fraction. This is a fraction. And what is this then? This is another fraction? And what's the difference between small f and big F? The digit f of the given? Oh, it's this is an input and this is the output, I presume. Okay. Okay, so this is like whatever we have, and I suppose this is the result. Okay, maybe it makes sense. And the difference between this is not greater than the error. Okay, it's not greater than the error. N is the smallest integer such that can like a can be true. Okay. All right. Each digit is output before the next is generated. It is never necessary to back up for correction. Procedure 1. The algorithm procedure is expressed in pseudocode. I think I'm kind of understanding it. We have used loop while repeat, blah blah blah. The loop exhausted. Okay, I think I'm kind of understanding it. Cool. So in this case, if b is a base, right? So we have to use 10 then. So we have to use 10. 10 to the power of n divided by 2. So we're gonna actually hard code this entire thing. Right, it's gonna be 0, 0, 0, 0, 1. Since this is the last digit, I'm gonna do it like that. I'm gonna hard code a lot of things for now, because I want to make it work first. And then I'm gonna divide it by 2. So I suppose I can put a comment saying that this has to be to the power of minus n. And n in our case could be, let's initialize it to something. N could be equal to 4, right? So this could be equal to 4. And this is divided by 2. Okay, so this makes sense. And then we are iterating. So there's also like a nested loop, I think. So there's like inner loop and outer loop. But this is only fraction, right? Is it not? Fixed point fraction output. It only output fraction. But maybe that's exactly what we want anyway. So, alright, so I'm gonna like literally code it like that because I don't fully understand it, right? So it's gonna be k equal k plus 1. Well, I mean, I can literally do it like that. So say we have to be it like this. Then we define u, right? So u is r multiplied by b, and b is the base, I think. What was the b? Oh yeah, so I see. So it's like input base and output base. Cool. It's input base and output base. So in that case, I think it could be like this. And in here, it is floor, right? It is floor. I might as well actually put it here. Oh, by the way, we probably need to change the title. So the code, what is squares? It's signum, I think. It's actually a fractional part. We need to change the title. Printing. Well, I mean, it's so annoying because I'm not going to be programming in C for very long. You know what? I'm not going to change the title because fuck that. All right. Because we're going to program that in assembly anyway. I'm just trying to understand how to make an algorithm. All right. So this is a U, and then R is going to be R multiplied by B. Yet again, might as well actually maybe introduce B anyway, just in case. Double B equal 10. And as they already mentioned, this thing is equal to x minus its floor. So we can literally do that. So it's going to be that, and then it's going to be r minus, we actually do it like this, minus floor of r. Okay, then we take m, b. Cool. So that only does that. Okay, and while r is greater than m and not that, we'd output this thing here. Okay, I don't understand this loop. Is that a nested loop or not nested loop? Because if it's a nested loop, we don't update anything here. So okay, they actually explained that somewhere here. We have used loop while repeat. Okay, so this is a single loop. All right, this is a single loop. The loop is exited from the while if the while condition is ever false. Thus, one may read while b as if not b then exit fi. The cases statement in the taken as a guarded if construction. All right, so I think I understand that. I think I understand what the fuck is going on. This looks really weird. Like what the fuck is that? I need to Google up algo loop while repeat. It's a really weird construction. Conditional algorithm control flow, BBC programming while. It's probably going to be very difficult to find any information on algo. Algo loop. Algo. It's impossible to Google anything. Algol. This is what I want. For loops. What was that? Oh shit. I'm sorry. What the fuck? I accidentally locked myself. Okay, so this is really strange. Yeah. I know. I locked my screen. That's okay. Algol, what was that? Loop repeat. Loop while repeat. Okay. I don't understand this part. So strange. It's a really strange construction. What the fuck? Like while that, is that like another action that you have to do before repeating the loop? Is that what it is? Like it's so dumb. Like holy fuck. Okay. So you check that. Construct credited to the loop is exited from while point if the while condition is ever false. Thus one may read. It's exited. Okay, so while acts like a break. But why do we have like colon here? Or is that colon a semicolon? And why it is indented like that? I have so many questions. Like, so dumb. Holy fuck. Boomer languages, am I right? So let's continue. Holy fuck, wasting my time. Yeah. There was like a time in software development that like we needed to have like many like loop constructions, like as many as possible with weird use cases and shit like that. Yeah, it's one of those, I suppose. Okay, so and if I can actually just do like a while loop like this one, because like it's really not good. So while true, if r greater than equal, maybe the guy programmed in Python. Okay, whatever. R is less or equal than 1 minus m, and that in that case I want to break. I'm gonna literally emulate that in construction. And after that, what we're doing, we're printing U. But what the fuck is U? Okay, so I'm gonna just do printf, just to see what is U, because I don't fully understand what they're trying to say here, right? So what is U? And that should be the whole thing, right? So in this case, if so there's additional thing here. If R is less than half, less or equal than half, we'll have to print LF U. If it is greater, we might as well actually do something like this, right? We have to do +1 then. And N is equal to K. Don't really care if it's equal to K or not, but whatever. Yes, it's supposed to be break if it's not, sure. So I don't think I need N, but I'm gonna print the N just in case. I'm gonna print the N. So and of course it's okay, so it's not for loop. So it has to be K and holy fuck. That doesn't help me to understand the shit, especially this boomer construction. Holy fuck. Cool. Let's try to compile this shit. GCC printf64c. So yeah, this could be true. What else? We need math. We need math. All right. So U. What is U? U isn't declared. Why U isn't declared? It's kind of strange. Okay, so I'm gonna do it like this then. Oh my god. So U. It's making it really complicated. Why are you making it so complicated? Okay. Cool. So we also need to do LM. Okay. All right. So it did something. Just stop asking question me. Okay. So what do we have? We have 31,415. None of that shit makes any sense, except maybe we printed something without a new line. Did I forget a new line anywhere? Please tell me I forgot a new line. I didn't forget a new line anywhere. Goddamn. This is actually very bad, but it's super close. It's super close to what I'm trying to do here. So in the compilation, one more time. In the compilation, if we didn't have 3 here, it would have been correct. It's 1415, and that actually worked. So yeah, that's pretty cool. So maybe because it prints the fraction. What if I make it like this? So this is going to be 0. What is it going to print? Okay, I think according to this algorithm, what we have to do is split these algorithms in 2 parts, right? So first, the first algorithm will print the whole part, right? And another one is going to be print the fraction. And this algorithm prints the fraction. All right, that's actually pretty cool. That makes sense. That makes a lot of sense. And I think I'm starting to understand that. I wish I could like actually refactor it so it looks a little bit better. Right, so we're trying. For example, if you have a bigger thing here, let's say if I put like 16 here, is it gonna print it? It actually doesn't print it, right? Unless I increase n. So if I add 2 digits to n, it doesn't include it, but if I add 4 digits to n, it still doesn't include it. That's really interesting. Oh yeah, I know why it is like that, because this. But we can try to prepare m. Yeah. So we need some sort of an algorithm that will prepare this thing for us, like minus n. But yeah, I really like it. I really like it. So m is going to be equal to that, and I think I'm going to start with m equal to 0, and then we're going to iterate like so, 0 through n, and yeah, so this has to be integer, plus plus I, m multiplied by 0, 1. So, and after that, we can put it like this. So m initially equal to this thing. M initially equal to this thing, and then we do m divided by 2, or maybe we can also multiply it by 0.5. So here it is. So here is the whole initialization of m. So it could be like this. So m has to be like this. So I'm gonna put n to 4 yet again, and now I'm gonna keep incrementing it. And as you can see, oh yeah, it's actually put 2 here, right? Even though our original one was 1, but this is because you have 6 here, so it rounded it up. It actually rounded it up. That means if I increase n even further, it actually prints 6. Yeah, there we go. It prints 16, like 14, 15, 16. Holy shit, it works, and it's actually super easy. Nice. I can make it maybe even bigger. Yeah, and it actually doesn't go any further, right? So it just reaches the end, and I can have 1 here, 1 precision here. Maybe I can have like literally 1 thing here, then 2, 3. Holy shit, it's so easy. So the thing about this algorithm is that you control how many things you want to see. You literally control how many digits you want to see. So it's pretty convenient. Yeah. And I'm not using any standard library, so I can make it compile without a standard C library, and it will work, except we need floor. So the only thing we'll need here, by the way, is floor. And how do you implement floor? We can truncate it though, instead of floor, since we're dealing with yeah, that's gonna be a lot of work actually, but we can make this thing work only for fractions that are positive, and then for the negative fractions we can create a separate issue that you know, we'll take that into account. You know what I mean? It's very interesting. Okay, so yes, so this is 1. I want to actually parameterize it with n, or like right here. So I'm gonna put like 3. I have an idea actually. Whatever. It's gonna be 3. There we go. So b is the radix. Not the original digits of pi, whatever. K. I don't really need K, I think. I don't really need it. So the only thing yeah, if I'm not gonna need the K, so we only need to keep track of this K if you want to know how many digits we managed to print, right? So how many we managed to print here. But since I don't really care, I just need to print some digits, so I might as well actually do something like this. So there we go. So I can completely remove K, and there we go. So that kind of works. All right. Floor. Okay. So we also have like this U, which is like the rest of this stuff. And you know what? I think. I think I want to turn this from post condition. Turn it from post condition to a precondition loop. I think I should be able to do that from a post condition to a precondition. So essentially, to turn it from a post condition to a precondition, we need to move the first iteration out of the loop here. So, and to do that, to turn it here, it has to be floor f multiplied by b, and r in this particular case is essentially f multiplied by b, but also floored. If you think about that, it's also floored. Because initially it's going to be that. So, and then while this is true, we're going to keep printing this thing and keep repeating this iteration here. Look how much nicer it is now. Like, like if it works, of course. I'm not sure if it works yet. So we have 3, let's put 4, and it doesn't work. So yeah, there we go. Okay, so let me see where I fucked up. Right, so it was somewhere here. Okay. Haven't finished yet. Okay, I haven't finished yet. All right, so this is gonna be like this. U is gonna be simply this, and B and R was essentially F. So you just multiply it by B, right? So as far as I can see, do you actually need to do that before? Okay, wait a second. So this is that. Then what if I move this single iteration like right here, and because of that I should be able to move this like that and like that. Like it should work in that case then. So I basically like just move this iteration like right here. So will it work now? Yes, it does work now. Okay. Okay. Oh, I probably forgot to do this thing. I see. Because of that, I should be able to move this thing here, so it's not needed anymore. So it could be literally like that. Okay. The next thing R is R multiplied by B, right? R multiplied by B minus floor R multiplied by B. There we go. So that's what we have here. But maybe it would be better to keep it like that. What the fuck is? Oh, I'm doing everything correctly. So if I increment the amount of digits I want to print, it should be working. So I'm just trying to minimize this entire thing. All right. Seems good. Seems good. But on top of that, like we wanna be printing this as integer, right? So we'll have to convert it to an integer. We'll literally have to truncate it. And since we're truncating it, it has to be like this D. Yep. D. And we'll also have to get rid of the new lines, right? Because, yeah. Print f new line. And, so this has to be int, and this also has to be int. There we go. So, and on top of that, before printing anything, we want to print f0. So print in f0. Okay, so that's our thing. And we can increment this entire stuff, and we're printing the whole thing. Cool. Still not fully understanding it. Still not fully understanding it, and it kind of bothers me a little bit. All right. If you multiply it in bar radix, okay. I should probably move on to implementing this in assembly, but it's kind of intimidating, to be fair. So because this is not a full, this is not the final implementation. That's the problem here. It's not a final implementation. You first need to print the integer, right? So you need to print the integer first, and then you can try to print the fraction. So we can call it like this. So this one is not going to be like 0, right? You will call it f64 frac. So this is literally what we're doing, right? And the actual print f64 that accepts a value, right? What it does, it prints I64, like it prints I64 by truncating the entire thing. So you literally take this thing like that, and you turn it into int, 64t, right? Like this. So and then you print f64 frac, and you do that by I suppose taking this and subtracting the floor of this, right? And this is the fraction that you get. So, and by doing that, and it's actually like we can also supply the precision, so we don't have to do it here. And then we should be able to print this entire thing. The next thing that sounds intimidating is FP registers. Yeah, I don't think it's that intimidating. We'll see. We'll see. I've implemented a lot of intimidating things, so I don't think it's going to be a problem that much. So yeah, people are getting bored. I should actually go into implementing it as possible. So yeah, I'm gonna actually stop it because we do have print I64, right? We already have print I64 implemented. And I'm gonna just do the following thing where I do pri I64, right? And I just print this entire thing. So that should work. That gives us the full thing. So it has to be int types.h, and there we go. So now you can actually print the entire stuff. I wonder, like, now let's try to work on getting rid of the dependencies, except print I64, right? So the floor, how would you implement the floor? So let's call it maybe, let's first of all remove math.h, and let's remove -l, right? Let's remove -l. So it complains about floor. Let's implement the floor. So it's going to be double floor. It accepts X, right? It accepts X. So, essentially, if X is greater than 0, right? If X is greater than 0, what do we want to return? We want to basically truncate this entire thing like that in 64T, right? We're doing an in 64T, and we're converting it back to the double, right? So, yeah. If X is less than 0, right? Actually, we can also make it like equal, just in case. This could be actually like this, so that means it's negative, right? That means it's negative. And in case of a negative, right, so if you try to truncate this entire stuff, right, you will have to -1 it, because floor of -3.5 is not equal to -3. It's actually equal to -4. I'm going to start banning people who says this is not assembly, okay? Because I'm testing an idea in C first, and once I test it, I'm going to move on to assembly. All right, so, yeah. So after that, this is going to be like this. It's going to be X plus 1. And then we're going to be converting it to double, right? We're going to be converting it to double. Okay, so that should be working, and that means now it does work. Okay, so it's working. This is how, like, literally the simplest implementation of a floor. We don't depend on a math library, which is great. Which is great. So maybe we can try to get rid of these printfs, right? We can try to get rid of these printfs. So let me see. We can try to use write syscall. But I don't think it's necessary, right? I don't think it's necessary. We can just... yeah, it's cool. Okay, so we literally implemented the algorithm. We implemented it. Okay, so we're good to go. By the way, I was thinking to actually separate the different implementations of different native functions. You see, I have this like print i64 here, and then I'm gonna have separate print f64. But I'm thinking is that I'm gonna keep all of them in a single file. I think that this is how I'm gonna go about it. So I'm gonna rename this thing into, this is not what I wanted. Print f64. I'm gonna rename this original thing. What will happen if you feed infinity into the print algo? Probably something's gonna happen. Let me finish my thought. Okay, so assembly here is gonna be called natives, right? So because I want to keep everything in a single file, right? And print f64 is going to be here, right? It's not gonna be in a separate file, all right? So we are doing organizational stuff. We're gonna think about corner cases a little bit later once I finish my thought. Okay, so where is that? Yeah, so I need to move this thing here. So note stolen. All right. Okay, so let me build. I don't know what the fuck is going on. Print i64. Why are you sending this emote? You wanna be timeout or something? Alright, so Basm to Nazm. So now we're gonna do this thing, natives. Right, so this is gonna be natives, and I think this entire thing is gonna be probably called, yeah, let me rename all of that. It's gonna be create replace natives. Right, like this. Gen natives. This is not has to be renamed, and okay. Really hate it. Like, so it's such a fucking unhealthy environment. Holy shit. You're planning to do something in assembly, but before you can do something in assembly, you need to test something out. And for like half of an hour, you are forced to listen to this bullshit like, boo-hoo, title, it says assembly, but they're programming in C. Like, I just switched to fucking C for a second to test thing out. Holy shit. And I knew that is gonna happen, and it happens every fucking time, and I don't know why it triggers me all the time. It's just, yes, I'm gonna program in assembly fucking soon. Holy shit, such a fucking toxic environment. Alright. I wanna make a cup of tea. Who the fuck are you? Never seen you in my stream, to be fair. Who the fuck are you? Alright, so I'm gonna make a cup of tea, and then we're gonna continue. Okay. I should probably start with a completely separate environment where I can test these functions, because I don't think I can easily test them. I can easily test them in the compiled program, right? So first of all, we'll need a floor and some other stuff and so on and so forth, right? Because of that, yeah, let's create natives test is gonna be awesome, and it's gonna be bit64, right? It's gonna be bit64 and segment is text, so it's a text segment global underscore start. So I also need this exit code. So I think I'm gonna copy paste some of the code from the example, from the Fibonacci example. Right, so specifically I need some of this stuff like syscalls and whatnot, right, because that's what we'll need at some point. And the only syscall I want to call right now is going to be just an exit syscall. Right. It's going to be just an exit syscall. I'm going to include this thing here, and what I want to include is natives awesome, right? So natives awesome. So yeah. It also expects, okay, so print i64 expects a stack. Which is mostly understandable, yeah. maybe I'm gonna start it like that. Okay, so I'm gonna just do floor here, and it's gonna be return. Okay. So let me try to build this entire thing. Build natives sh bin sh. So let me go to test. It's not test, it's build x666. Delete it already. Okay. Natives test. Why do we even have linkers? They make everything complicated. Like, I really hate how to build an assembly program I have to do that in 2 steps on Linux. I think this is a complete fucking bullshit. Like, I don't remember doing that on Windows when I programmed an assembly on Windows. I think it was easier on Windows. You would literally... I think it probably was kind of the same on Windows, but like... What the fuck? Why do we even need that? Like, linking is such a like weird step that I never understood. Okay, did it do anything? I think it did. I forgot to enable the tracing and stuff like that. Forgot to enable the tracing, so this is not really what I wanted to call build natives sh. Okay, so this is what we have here, and here is the executable. Yeah, so I can test these ideas out. I think I forgot to pour some water, so I'm gonna go back to the kitchen super quick. I just realized that water is not ready yet. Okay, so let's see. Let's see. Print f64. Okay. So how are we gonna pass the floating point? As far as I know, there is like a convention, x86-64 convention for floats as well. Linux x86-64 call convention. So what's the first floating point register that is used? Not x86 calling convention, I want x86-64. 64. Alright, Microsoft, don't care. Yeah, systemd, AMD. Okay, XMM0. Alright, makes sense. So yeah, these are integers registers, and all the integer arguments are passed through them. But floating point is going to be passed into like XMM0 and so on and so forth. And floor, okay, and result integer return value to 64-bit values. Okay, floating point returns values similarly stored in XMM0 and XMM1. And what does it mean? And you have to return like several of them. Binary indentation. Like why did they say and not even or anything like that? So it has to return like 2 of them. Is that what it like? Why is this and? This and confuses the hell out of me. What is that supposed to mean? Does anyone know? they're similarly stored in Excel. They also, does it not make sense? Are similarly stored integer return are stored in Rex values up to Rux and oh, okay, so yeah, I probably skipped this sentence, yeah, because I was specifically looking for floating points, and I skipped this sentence, and I like, who writes it like that? Oh my god, why do you write sentences that depend on previous ones? Why? Oh my god, it makes it difficult to read. Like if you have like too many interconnection between the sentences, you cannot isolate the sentence and extract information out of it. Like it's so bad. Right, like I cannot parse this sentence without reading the previous one, but I don't care about the previous one because it's about integers, and I don't care about integers, I care specifically about floats. So dumb. Anyway, so we accept, so they are actually accepted through XMM0, right? So this is what we have here. Okay. So NASM x86-64 truncate floating point. So let's actually see, like converting floating point to integer with truncating instead of. All right, feast p. The feast p instruction changes 0 to 7 because of rounding. I want to turn 0 not 1. Okay, so there's some. Okay, it doesn't even work. This website doesn't even work. You truly have... Okay, so if you're using SSE instructions anyway... alright, so if SSE... Alright. Feast TP instruction, okay. So they're talking about this... instruction feast-tp store integer with truncation. That's actually pretty cool. So converts the value in st. What is st? Into assigned integer using truncation chop as rounding mode to transfer the result to a destination and pop st. All right. So I wish there was an example. So does it use like some sort of a like stack structure? On the FPU or something like that. I think that's what's going on here. I think that's what's going on here. Yeah. Okay. Feast TP example. Oh my god, this is that because of my dark reader? Is that because of the dark reader? It could be because of my dark reader. Yes, it was because of the dark reader. What the fuck? The FP instructions covered in this chapter perform no mathematical operations on numerical data. Their main purpose is to simply transfer integer data between FPU's 80-bit data registers and memory. Integer data cannot be transferred directly between a CPU and FPU. The integer data transfer instructions are field feast, feast p, feast tp. Okay, so all right, field. So everyone's talking about feast TP, so this is probably what I'm going to use. So this instruction is the same as feast. Okay. Instruction is the same as feast. Oh fucking hell. The instruction rounds the value of top data structure register st0. It would be pretty cool to have like an example that actually works. So they have examples of using the hand coding to store the value of st0 as truncated d-value could be as followed. This is not what? How is this an example? They're not even using neither of these instructions. Like, how is this an example? This is not an example. This is a really bad example. Okay, store integer. Like, I specifically asked for an example. Could you show me like an example that actually works? Okay, so this is probably what I wanted to see. Right, so here's an example, right? So you do something FLD API, then you push EIX, then you do that and do that. Okay, so this is like a full example that we can work with. So for example, I can now Google this instruction, right? So this is the examples I'm looking for, right? So just a full example with the context, because these kind of explanations, they miss a lot of context that I don't know. And if they give me the context, I would probably Google it up. Right, for example, what is FLD API? Okay, let's actually look into that. So you see what I'm talking about, right? So like you need this kind of context. Push one of the 7 commonly used constants onto the FPU register. Okay, that's actually pretty cool. So we have a built-in constants in the CPU. That's actually pretty cool. Isn't that amazing? I think it's actually kind of cool. So we can do FLDPI. Oh, okay, I like that. So if I try to do FLDPI, so it will push this thing onto the stack. It pushes that onto the stack. But I'm not sure if it's all gonna work. I might actually doing this correctly. Is it work on? Does it work on 64 bits? Imagine TLDR utility, but for various docs. Nah, it's not gonna happen. Nobody programming in assembly. Nobody gives a shit about this language. Okay. So, FLDPI. I wonder if there's like a way to inspect the FPU stack. For example, okay, so if I try to compile this entire thing, right? And then I do something like a GDB, GDB native. What? Whatever. Break start, break start, run layout awesome, right? So, and then you can do something like registers, but can you do anything else? Is there like FPU? Okay, so there's a registers, GDB, FPU stack. Is that a thing you can inspect? How to print registers? Oh my god, FPU. Okay. All right. For all registers. It's something about ST0, ST1. What are the ST0, ST1 and stuff like that? Are they the stack? Okay. FPU stack. I think I need more information about FPU stack. Confusion is the top of the stack. Okay, I know that I'm not gonna get that answer, but I need a simple answer, yes or no. Are the registers also the stack of FPU? Simple answer, yes, no. Or maybe, okay, third one, not really. So I expect one of the three, yes or no? Okay, so yes, thank you, I see. That's cool. So I don't need any more information about that. That's the whole information I need about it. I don't need like a lecture about this. Okay, so ST is also the stack, and I wish I could actually look into it. Like how can I inspect this stuff? So you can do info all registers. Okay, so that means I can do something layout. How do you disable layout? So we can enable layout, but there's no way to disable it. Like, I know that you can do to disable, but then, yeah, that's how we do that. That's how we fucking do that. Welcome. It's no layout. No, there's no such thing. You're debating me. Okay, so info. Can I do FPU ST stack? Okay, info all registers. What else can I have here? What all registers? Can I say FPU registers? Is that a thing I can do? What the fuck is going on? This is not what I wanted. Info, if there is all register, there should be FPU registers, right? There's no such thing. So the only option I have is all registers. And this is not convenient because I have to spend too much time to like scroll down to see this thing. I only want to see this stuff. So in 4, is there any other way to do that? Like GDB print ST registers only. Google becomes dumber and dumber. Like it becomes more and more difficult to like actually find. Okay, registers. Okay, so there's in 4 registers. Okay, and you can look at specific registers. Cool. Can I look to the group of the registers? I cannot. If I provide 2 registers. Okay, so they're telling me to look at the whole set of the stack registers. I have to do this shit. Is there any way to make it shorter? Does anyone know how to make it shorter? IRF. So what is F? Like, I don't care about making these things shorter. Like, first of all, these 2 words doesn't need to be shorter. You know why? So, because I can just autocomplete them. I don't need to make them shorter. It doesn't save any time, okay? So what is F? Okay, that's a little bit better. But why it wasn't... Okay. Float. Oh, it's a float. I see. That's a little better. Thank you so much. So it could be just that. Alright, so I'm gonna step 1 instruction. What the fuck? I didn't want to. Okay, I stepped 1 instruction and now I can do in 4 registers float. Okay, I have this value on the stack. Alright, that is super cool. Now, what if I want to put something else? Is there something like FLDE? How is that a common constant? Wait a fucking second. So there is FLDA pi, FLDA 2e. It's called 2e. Oh, it's a logarithm. Okay, so let's put 2e. So actually, it doesn't even print anything. FLDL2e. Okay, so I want to put several of them and I want to see how the stack modifies. Right, so this is literally what I want to see. I want to just see how like stack modifies and stuff like that. So all right, so this is gonna be like this. Break start. All right, break start. We're gonna run it and I'm gonna do layout awesome. And let's take a look at the info registers float. You don't need to make it shorter. Tab, just press tab. It's not that hard. Come on. All right, so this is that, and yeah, quit. Then next one. Okay, here's pi. Next one. Okay. So yeah, they're pushed back. So, and you have a stack of 7 values, right? You have a stack of 7 values. Cool. How can you push more shit onto the stack? Is there any instructions that do that? So you can do FLD pi, and I would assume that you can do now the shit FLD, just FLD, where I can put anything like 69 and then also 420. Will that work and will that compile? So let's actually find out. Expression syntax error. Okay, so x86-64 FLD instruction. How do you use that? Load floating point. So what do you expect from here? Floating point exception. What does it take? Pushes the source operand onto the FPU register stack. The source operand can be single precision, double precision, or double extended precision floating point format. Cool. So expression syntax error, and I wonder why it didn't work. Is that because it's something with the NASM? Okay, NASM floating point numbers. How do we do that? How do we do floating point numbers in NASM? Okay, so I don't see, like, specifically. Okay, that makes sense. Quarter precision. Yeah, here they are. So, okay, so there's this thing. Is that what I have to do? Invalid combination of opcont and operand. Okay, I just need an example. NASM FLD. How do you do the FLD in NASM? Just show me. Just show me simple example. Just show me. Come on. It's not that hard. FLD, D word. Okay. So it pushes them from the memory. It pushes them from the memory. But is that what I want? What is this resource actually? Is there any extended value? Does it have to be in the memory? Does it have to be in the memory? Okay, how can I put an immediate one? FLD immediate. How do I specify immediate floating point number? FLDL. I don't know of an assembly language which supports literal floating point constants for immediate use. The usual means is to declare initialized storage containing the floating point constant and reference it. Okay. So this, speaking about FLDL, I don't have FLDL, but because it's AT&T. It feels like the answer is no. Except maybe there's a way to put an immediate value, so we can put F. Okay, this is what they're doing. They're doing like S0 and shit, but this is not like pushing, right? Oh, really, I think x87 supports loading 1 and 0. I mean, who cares about that? But can you like do something like FLDL? Let me see. Rex. Come on, bruh. Okay, you cannot. Alright, so segment doesn't support immediates. I will. Thank you, Captain. Okay. Alright, so DQ, I suppose. Let's push something there. It's gonna be, and NASM does support, I suppose, floating point const literals. Is it a keyword? Yes, it's a keyword. Cool. What's gonna happen if you try to overflow this thing? So there's a 4, and let's put more of them here. What's gonna happen if you try to overflow that motherfucker? Start, run, layout, ASM. Let's see. Okay, so info registers float. So did we lose some information? I don't think we lost much. It already contains 8. Okay, I'm an idiot. So let's actually put y here. It's gonna be 69. All right, it's gonna be 69. FLD y. Right, and it has to be keyword. Has to be keyword. Cool. Has to be keyword. Yep. Let's recompile one more time. Break start, and it's gonna be we're gonna run it. Layout assembly, and let's go. So let's see. And last one. Nothing happened actually. Does it get overwritten? Info registers float. Okay, that's very interesting. So we have a none on the top of the stack. We have a none on the top of the stack. None of on the top of the stack. But if I didn't overflow it, would we have a none on the top of the stack? That's a good question, actually. I'm really curious. I'm really curious if we had a none on the top of the stack. This is not what I wanted. GDB is a piece of shit. Okay. Okay. So I'm pushing it here, info registers float, and okay, so it's interesting. If you're overflowing, you're gonna end up with none. I was thinking that maybe it's gonna actually start removing the values, but it does actually remove values from the stack. It's just like it gives you none. That's very interesting behavior. Maybe it's something with the debugger itself, but I just wanted to check that. Nonetheless, just wanted to check that. Okay, so essentially, if you have something like a value for 20, right, 69, right, so here's your for 20, 69, and you push it onto the stack. So it's going to be keyword X, whatever. Then we can use this one of the instructions that we were talking about, right, to feast this entire thing out of the stack. You know, feast the thing. All right. So remember how we were talking about this one? Yeah, this is what we're talking about. So feast TP. So FLD field D. This instruction decrements the top pointer and loads the register value from the specified source in the new top register. Okay, so this is feast. Rounds the top to nearest, and okay, so it accepts destination. We can feast it into racks. Let's try to feast it into racks. So we are feasting it into the racks, an invalid combination of operands. Okay, so we cannot do that into racks. I suppose the destination has to be a memory. Let's actually assume that it's a memory, right? So I'm gonna have DQ, and it's gonna be initialized with 0. Can I say that I'm gonna feast it into Y? Is it possible to operation size? Okay, so if I provide keyword, a valid combination of code. Okay, so how do you feast it then? If feast expects the destination, right? Okay, so it doesn't really have to be. So they expect a okay, so it has to be in one of these. All right, let's go back to this example. So ESP. Push EAX. It's very interesting. It's not particularly convenient. It's not particularly convenient. Int var stores the truncated value st into the variable int var. Well, that's kind of what I tried, but feast was, what was that? Feast TP? Let's try this one. Invalid combination of opcode and operand. It doesn't work. It doesn't work. Interesting. Interesting. So let's actually read about feast in general. Stores their C field nearest integer according to the rounding mode. This instruction cannot store the value of st as that. If the st data register is empty, both stack don't care. If the round blah blah don't care. If the actual value does not change the instruction. Example of usage. Okay, so store the rounded value of st as a word at the memory address indicated by that. Store the rounded at the memory address indicated by that. So I have a memory address. Here's the memory address. It should work, but it doesn't work. So I don't understand. And NASM doesn't really explain much. Invalid operation code or something. Okay, let me try to Google NASM FIST TP. Right, so support for FIST TP. So what? That's not really promising result of the Google. What the fuck? Excuse me. I'm trying to assemble code with the fuck. Apparently it was introduced with SSE3. Okay, so do you work FIST TP? So they all kind of like using this through the racks. Are you serious? Do I really have to do this very dumb shit where I have to like do it like that? Really? Holy shit. Okay, so somebody suggesting to actually do it like this. Is it gonna work? It's not gonna work. You have to do that through a register. Holy shit, okay. So literally have to do that through a register. I mean, it's assembly after all. I mean, what did they expect? It's an assembly after all. All right, so let's continue. The next thing is going to be that. So I'm going to break at start. So move AB, so this is what we're moving, and then first I want to take a look at the position of Y. All right, so here's a Y. We're going to treat it as a pointer, then I'm going to do long unsigned int. So here it is. Here's a very long unsigned int, and it contains value 0. I might as well actually do display. So after fisting this entire thing, I should have what? I should have 420 without 69 at the position of Y. There we go. We truncated this mother flipper. How about that? How about that? Right, so we pushed it into the floating point and then we loaded it back. We fisted it and that thing got truncated successfully. Isn't that amazing? Isn't that amazing? I think it's goddamn amazing. Yeah. So yeah, it's kind of cool. What about the negative part? So if this thing was negative, for example, will it be truncated as well properly? So let's find out. We're about to find out. Just be break start. Okay, so did I? Oh goddamn! I already lose the information. So unsigned int long unsigned int. It's gonna be pointer to Y. And we're gonna do that, and I'm gonna do display. All right, so we're moving this thing and we are moving it back. That makes sense. Okay, so if I print this entire thing not as unsigned one, okay, it got truncated correctly. So this is literally truncate. I really like that. So this is exactly what I need here. Like literally, that's kind of cool. We might as well actually implement something like this. Maybe truncate. I know 64, F64. Let's call it like that. So, and what do we accept? By the way, what about XMMS instructions? Like, so I mean registers. So these are like floating point registers and shit like that. Is there any instructions that let me work with these registers instead, like on the level of floating point? I think they're sort of like a part of SSE. is it necessary for me to work with the stack operations? That's what I'm trying to find out. Is it necessary for work with this stuff? And now you can move directly to them. Okay, cool. But then if I want to truncate something in XMMS 0, like to integer, how do I do that? Okay, so this is like a stack truncation. It feels like, okay, maybe we can Google that, XMMS 0 operations. So maybe it will find something. Macro with FPU operations. Okay. Like, do I have to use these stack operations for truncation or not? SQTSD. Okay, this one is interesting. MoveSD, XMS, SQSD. Okay. Okay, float, truncate. Oh, it's not XMMS. How to truncate values in XMM register. All right. So, okay. All right. So I think it's a very old way of doing that, right? So round packed single precision floating point values. Round the 4 single precision floating points in the source operand, second operand using rounding. Okay. Okay. Is there any example? Converting, but I don't need to round. Is there like floor? Floor, not really floor. Round PS requires SSE 4. Really? God damn. Oh, Jiang, you're here. Welcome, by the way. Welcome. Hello. Did you finish your lecture stuff? Convert with truncations, scale double precision floating values to sign integers. Thank you so much. So what we were trying to do, we were trying to do it like literally with fisting and loading onto the stacks and stuff like that. I think this is like an outdated way of doing that, but at least it feels like, right? So I think in a modern x86, you don't have to do that. Like you can just like use these kind of things. Mostly, yeah. Okay. So convert the double precision floating point value in the source operand, the second operand, to the single double word integer in the destination operand, the first operand. Holy shit! I mean, that's exactly what I needed. Thank you so much. So can I now move XMM 0, and I want to move like 42069? Is that a thing we can do in 2020? Expression syntax error. What was that? Is it MoveSD? It's not immediate, only from memory. Okay. You're wrong. Or maybe you're not wrong. No, it's literally invalid combination. Nope. You don't know what you're talking about. All right. So move into XMM 0. Move assess. Okay. What are you googling? Why am I listening to the chat? Just stop. Okay. Is it really not supporting immediate? Okay, I'm gonna check it because I don't trust chat. Okay. So for the registers you don't need the keywords, but I'm not sure if I put a keyword here, will it still work? Aha. So what's the size of XMM 0? I think XMM 0 is actually quite huge, right? So it's bigger than 64 bits. Right, size of XMM 0. It's not 90. Okay. So I remember that. How do I access the other half of that thing? So how can I put it? All right. Let's probably I have to use another register. Let's take a look at the example. Yes. Not a single example. Try. Okay. Just an example. This is C. You know, the thing that people say in my chat. Ah, you said you program in assembly, but this is C. Re. Yeah, that's literally me right now. Okay, so just an example. Like, why is it so difficult to just provide an example? Like, I'm pretty sure it's not that hard to implement that. Okay, I don't care. This is the next step, Jiang. This is the next step. The first step is moving this memory. So here's my concern. This size is 128. So, but I allocated 64 bits. So that means this operation actually reads this thing into the memory as well. So how do I prevent it to read over? So that's what I'm thinking about. You suggest in the next step. Okay, I do agree with you. Right. I do agree with it, but nope, it doesn't. But it's 128 and this is 64-bit. The operand is 4 byte wide. 4 byte. Do I not understand how MoveSS works? Alright, so that means I can do that and it will compile. If you are right, if I do that, this will compile. Okay, you're right. So you're gonna get VIP. So okay, that's cool. Thank you for being in the chat. Holy fuck, because so many people like have no idea what they're talking about in the chat. Like so appreciate you, Jiang. Seriously. Yeah. Anyways, because like they think they understand what's going on the screen. In reality, they have no idea what they're talking about and what's going on the screen. You're like one of the rare people who actually understand what's going on. All right. So yeah. Now that makes sense. Okay, so even though this register of the size 128, the operation itself reads like 4 bytes and whatnot. And that means it reads this thing incorrectly completely. Right. People love to backseat assembly when they don't know what is going on. Yeah, it's really strange. But what if I want to move 64? That means I'll probably have to use a different instruction here. So let me see. Scale a single precision. Okay, S, and I would assume that you will need SD. Right, and that will not compile. And then if I put Q word here, that will compile. Okay, I see. That makes sense. So SS stands for like last S stands for single, and last D stands for double. Okay, now that makes sense. Now we can move on to that scary instruction. Now we can move on to that one. Okay, let's Google it up. So, convert truncate double precision. Cool. So this is going to be like that. Source operand, second operand. So this is going to be this XMM0. So this has to be a source operand, the second operand, and single to a single double word integer in the destination operand, the first operand. Okay, so if I put racks here, will that work? It does work. Okay, that's pretty cool. And that is actually way simpler than using stack and stuff like that. So I really like that. Well, maybe we're gonna use this one. Thank you so much. All right, so cool. Let's break. This is not what I wanted. Break start, run, and it's gonna be layout assembly. So I probably can maybe also gonna do registers, and XMM registers are not visible here, so it's absolutely useless. In 4 registers XMM0, we can take a look at its value. Okay, cool. So the next instruction, we're moving this thing And what we have in the registers. In registers we have some stuff, and our debugger doesn't even help us to understand what's inside of it. This is very exciting. I really like that. Anyway, so I'm gonna do the next instruction, and in here we have minus 420, exactly what I expected here, so it truncated everything correctly. Cool. Thank you so much. That's actually very cool. It's actually very cool. So it's way better than the stack situation. So stack no stack. There we go. Cool. Stack and no stack. Jiang, you didn't see a pretty cool thing we implemented. We implemented a print F64 without printf. Well, I mean, I technically use printf, but I don't use like LF or any F or anything like that. So we implemented the algorithm that actually prints the fraction. So we have print F64, all right, and what it does, it first prints the whole part, and then the fractional part. And from the fractional part, we just stole some algorithm. So, and we can take a look at that. So if I do gcc printf 64c, and then I can try to run it. A out, it does print 3.1415, and potentially it doesn't even depend on libc. So we will be able to print floating point numbers without libc, libm, or anything like that, because the only function from libm that we need is floor. You should apply to get into... Nah, I don't understand how this algorithm works, because what I literally did is I stole it from... oh my god, wait, give me a second. I stole it from here. So this was the article, and by the way, this article was talking about some sort of like a very precise algorithm, and they provided like a very dumb Pepega algorithm as an example of a very dumb Pepega algorithm. And what I did, I implemented that Pepega algorithm. So I implemented this one. So this one is a fixed point precision, so you need to specify n, you need to specify precision to print it, right? So, and this is what I did, this is what I implemented, and that actually removed the dependency from libc and libm, which is actually pretty goddamn cool. But I still don't fully understand how it works. I kind of like roughly understand, but yeah. What's up, Outnet? Welcome to the stream. All right. I closed my whole browser and lost all of my tabs. Nice. Which is probably a good idea because I wanted to close them anyway, so whatever. Okay, what I was doing, let's go back to native test assembly, and now we have a truncation that works exactly as I want it to work. Cool. So what we're doing, essentially, we're translating this implementation to assembly, right? We're translating it to assembly. Don't you love the MQ destroys your entire life? Yeah, but in my other account I have important tabs pinned, so it's not that big of a deal. Alright, so Floor will accept the argument through XMM0, right, input, and the XMM0 is going to be also output. As far as I know, this is the x86-64 System 5 calling convention, right, if I remember things correctly. Okay, so we have this thing in XMM0, right, and to be fair, so let me actually comment it out, and I'm going to move SD, cool, Q word X, and then I'm going to call floor, and then we're going to explore the floor there. Cool. So how do I do comparison? XMM0 CMP. XMM CMP 2 32-bit floats. Is that even possible? So what's going to be the thing? I'm trying. So what's the instruction? You want to use the JB and JI instructions instead of, well, this is not what I was asking. So SSE, CMP, okay, thank you, CMP. I think I'm starting to notice a pattern. Okay, so first S stands for SSE, I suppose, and then we have a size of the scalars we're working with. Okay. Is there a test SD? X86. Probably not. Okay, but that's cool. Compares. So and it works similar to CMP as well, right? It works similar to CMP. There's also CMP equal SD. Oh my god, you can actually do so much different shit. Holy fuck. Okay. CMP SD. So what does it accept? Compares low double precision floating number in second operand with the first source operand and returns the value. Okay, so can I use immediate shit here? I'm pretty sure I cannot use immediate shit here. Please tell me that I cannot do that. Please slap me in the face. I want to be slapped in the face with no, I don't think so. Yes, thank you so much. This is exactly what I wanted in my life. Alright. Wait, do I... Like, every time you work with floating points, you literally have to have a little bit of memory allocated for these kind of situations, for loading things into the... That's very interesting. So... Huh. Okay, that's interesting. There's no way to encode an immediate floating value. Alright. Makes sense, I suppose. So that means we can have like a segment at BSS that indicates segment at BSS that indicates the 0. And we can allocate like some 0 here, right? And this is what we're going to do here. It's going to be 0 keyword. Please slap me in the face. Thank you so much. Okay, CMD operand combination size is not supported. Attempt to initialize memory, ignore. Oh, yeah. So it has to be rescue. It has to be rescue. Cool. And there's a second one. Wait a minute. Who are you? Pepper Pains. Okay, so didn't work. Sarah Moon, what's up? How are you doing? Welcome to the stream. Really glad to see you. So, I think something doesn't really work. You need a third operand. Okay. Let me see. Compares there is a second and first operand. Returns the result of the destination to the destination operand. Could it be any operand? Or... Okay, I need an example. But obviously I'm not gonna get an example from here. CMPSD. Oh, by the way, I know how I'm gonna title this stream. Just a second. Yes. Well, people who actually sit in our Discord server will know this reference. Programmer. What was the... Okay, so let me go to the Perl subreddit because I forgot the specific wording. The specific wording of the title. Okay, wait a second. Just a second. Only... Oh my god, it's so slow! Holy shit! What did they do to the Reddit? Using only... Programmer tries to write assembly... Right. Tries to write ASM program just using Google. Okay, so that's a perfect title. This is what I needed in my life. Yes, that's exactly what I'm gonna do. Yes. Okay. Yeah. CMPSD. Do we have something like do we have ASM doc or something? Do I have to read ASM doc? Maybe that's what I need to read. It's the table that you keep scrolling past. Really? Which one? I'm moving too fast. I'm really sorry. I'm so sorry, Jiang. CMP is D. No. It's the table I keep scrolling past. Is that one? This is the different CMP as D. How is that an example? Is that an example? It doesn't look like an example, that's the problem. It barely looks like an example. It looks like a definition or something or whatnot. So you need to put the third number. Okay, like I got it, but what do I put there? Like, do I put this thing here? Like, what do I put here? Like, I don't understand. So that's why I need an example. Okay, so I have this stuff here. Wait. Wait. Okay, can I then do it like this? Why do you even need the third operand then? No, I cannot do that. Okay. And I still cannot do that as well. So none of that works. That's interesting. It's probably because of this thing. Okay, so I'm gonna try to move SD XMM1 like this, right? And then it's gonna be XMM1, and then I can do EQ and got Cooter, by the way. I figured it out. So we don't need any magic numbers. We don't need any magic numbers. Thank you so much. So equal, and what is it doing then? All right. So, what's next? Does it set any flags or anything? That's really strange. Like, what the fuck is this shit? You're not an Node9. I hope you don't feel bad about the stream. So. I hope this stream is not the cause of you feeling bad because me being Pepega. So yeah. All right. So let me see. Compare. So does it set anything? The comparison result is quad word mask of all ones. The comparison result, but where is the third? The comparison is quad word mask of all ones comparison and all zeros false. And where is it stored? Where is it stored? I need an example. I need an example. And by example, I mean not a single line, by the way, not a single line, but the full context. The full context. How you load up the things, how you call this instruction, and how then you branch. I need the full example. This is what I'm looking for. I'm like, out of the context, none of that makes sense. Like, all of that starts to make sense only within the context. So, yeah. Okay, so where is that stuff? Okay. No, I'm not doing that, sorry. More, just a simple example, please. I beg you, just a small example. Like, I don't even ask for too much. Like it's literally 3 lines. Loading the registers, calling the compare, processing the compare. Like, literally processing the compare. Okay, we already looked into that. CMP-SD. Okay. I need the context. Okay, holy shit, okay. Alright, so CMP-SD. And they even call it without any fucking operands. How is this an example? Excuse me? How is this an example? You need to Google SSE CMP SD. Wait, is there like different? What? The fuck is going on? How? What? Okay, where's my tea? I'm gonna make a cup of tea. One is a string one. Ah, I see. I see. I'm sorry. I see now. They decided to have two different instructions the same. Well, I mean, I suppose it's a huge company with very poor communication. So that's basically what happens in very big company with poor communication. You essentially get two different instructions with the same name. All right, that's fun, I suppose. That's really fun. SSD example. What's the point of MMCMP instructions, SSE instructions? Maybe I really have to just do Godbolt. Okay, we'll just do Godbolt. I don't want to do Godbolt because it's probably not going to generate the code that I actually need. It's probably going to generate something completely fucking pepega, like num less than 0. This is not what I wanted. Return 69. Show me what you've got. It's even compilation error. Okay, come on. Whatever. Double. Okay. I mean, you see, it doesn't even use CMPD or whatever, so Godbolt is not really that useful. Does it? Maybe this one could be useful. Compare scalar order double precision. So it could be useful actually, maybe. Swear to God, people. Speaking of, you know, trying to understand what's going on the screen and actually helping. So this sets flags register, it's better, I think. Compare, and it just accepts, so yeah, alright. So maybe Godbolt was useful after all, who knows. Alright, so this one is that, and if it's equal to 0, right, if it's equal to 0, we can do some jump. Hey, should we use new opcode space for this new instruction? There's some unused space in the CMD space. Use this one, should be enough. Yeah, probably. Anyways, so it's just literally like CMP. Right, it's literally like CMP, but it sets the E flags, which is cool. All right, so equal. If it's equal, it's actually greater. Right, if it's greater than 0, greater or equal, integer, but we, okay, greater or equal, so I think we want to escape, actually escape negative, right, so we're gonna have like negative here, negative, there we go. So if it's less, we go to the negative. If it's not, we go to the positive, and XMM0 has to be truncated. And how do we truncate all of that? We truncate it like this, right? We truncate it like this. To be fair, we can truncate it always, right? So we essentially truncate it always, and then we can compare and do something about it. So if it's negative, we always have to subtract 1 from Rex. We always have to subtract 1 from Rex. Right, and otherwise, what's another thing we want to do? Okay, so now I need to now I need to cast integer to float. I will need to opposite one. Okay, so let's actually. I forgot the last thing, right? Integer to float. So we have something like Rex here, like 69, just 69, and how do I convert that? x86 SSE integer to float. Convert short integer to float SSE. Well, yeah, classic. I especially like this thing, the Intel intrinsics that are literally instructions of the CPU have completely different names from the actual instructions that are used underneath. Holy shit, Intel, what the fuck is going on with you? Like, fucking classic. And this information is completely fucking useless, so unless CVT2, okay, thank you so much. How do you find all of that, or do you just remember all of these things because you worked with them for so long? Convert double word integer to a scalar precision. Okay, thank you so much. Yeah. Do you just remember all of these things? Oh, I think this is like a mnemonics. So CVT, right? CVT convert single integer to single SSE integer to SSE double. Okay, so convert. Well, I'm not sure about T though. T probably stands here for truncate, right? Convert truncate, truncate, not round, truncate SSD double to, I guess SSD integer. I'm not sure why do you need SS here, but I guess they may be useful, but yeah. So T probably stands for truncate, and that probably means that maybe there is an instruction that has round. Doesn't really have round, but maybe something else. Maybe just without truncation. Yeah, there is a version without truncation. So convert double in the source code in a single destination. Okay, that's very interesting. So, but without this thing. All right. Just remember move AX, move 0 to X. All right. So don't worry about that, by the way, because I'm gonna forget that after the stream anyway. So yeah, convert SI to SD. So, and I suppose now the destination has to be XMM0 Rex, right? And that should compile. That should compile. I once worked with this stuff, can't remember anymore. Yeah, it's actually very interesting. I worked with so many different technologies over pretty long period of time. It's not that long, so it's like a medium like period of time, like 15-16 years. And my brain went into the mode where it basically doesn't remember anything, but I just quickly learn what's needed to solve the problem. I solve the problem and I forget everything. So I just allocate the memory, load the knowledge, use the knowledge and deallocate that memory. So this is how it works all the time. That's why I can never remember how to do things in different languages, but I can program in so many different languages. As long as I have Google, though. Arena-based brain. So it's really strange. So sometimes I look back at my projects and I don't understand how I make them, because all of the knowledge that was needed to build those projects is already long gone. So yeah. Okay, so let's continue. So this compiles. All right. We're comparing these things. And after that, I'm just printing them back, I think. And that's what I do in these cases. Yeah, it's kind of dumb. Just a second, chat, just a second. I need to... Okay, this is a Rex. And if we're comparing them with 0, right? We're comparing them with 0. And if it's greater, skip deck. If it's greater or equal, we skip deck. Right. I want to actually call it skip deck because it doesn't. Right. Greater than equal skip deck, and then I can do something like this. Goddamn, I forgot. So convert to here, and there we go. We implemented floor. I think we implemented floor. This is the whole floor. That's pretty cool. Nice. It's actually a very small implementation of floor, not gonna lie. Interesting. All right, so I think we don't need to do that anymore. We can remove all of this knowledge because all of the knowledge on how to do all of this shit is already encoded in the floor, so I can just keep it like that. Cool. So I need two numbers here, pos and negative. It's also instruction. Maybe let's go plus and minus then. DQ is going to be 420, 69. 420, 69. Okay, so we're gonna do move SD XMM 0, and it's gonna be Q word plus, and this is gonna be minus, and then we're gonna call floor, and then we're gonna call floor yet again. So now we're gonna have like official implementation of a floor. Isn't that amazing? I think it's goddamn fucking amazing, mate. All right, so we're gonna break on start, run this entire thing. Is gonna be assembly. Okay, so I think I need to, is it possible to display XMM all the time? It's not that useful. It's not that useful. Okay. Just a second. Is it really floor, not trunk? Yes, it is really floor, I think. So essentially how we do that, if it's less than 0, we decrement it by 1. Make sense? So this is really floor. Okay. By the way, if you don't want to have memory for 0 constants, you can use XOR. That's actually a pretty cool idea. XOR. Okay. Nice. Thank you so much. That actually makes it self-contained, so it just can do that. Yeah. I used to program in assembly long time ago on Windows, and like I never expected that I'm gonna have such a long instructions, but I mean, okay. Alrighty, so let's try to Man, like 16-bit assembly was so much simpler. B-boomer clap. Alright, so run layout asm. And I want to print XMM0. Info regs XMM0 registers. Yeah. Is it possible to make it print like a floating point format? Is it even possible? Alright, so GDB XMM0 print float PF. Okay, so I mean it has to be a register though. You see, so P doesn't accept register. That's the problem. Oh, you can do it like that? Okay. Oh, it's AT&T. Okay. No? No? It's really sad, actually, to be fair. But, okay, maybe it's because it's 0, right? So I'm gonna step one step, and I'm gonna just take a look at what we have here. Oh, okay. So, oh my god. Oh, here it is. So I have to look into that. Is it possible to only see version 2 double? Oh shit, you can. Alright. Can I now also display it like that? Oh shit, I can. Nice. Alright, so here we go. We have that, and we're gonna step the floor, and it truncated it instead of taking a floor. What a shit instruction. So it's supposed to be actually have 421, so it didn't decrement it. That's very strange, but okay. So let me see. I'm moving this entire thing to Rax. Then I initialize XMM1 to 0. Then I comparing this thing, and if it's greater or equal, I skip the decrement and I do this thing. You need to move it from Rex back to XMM0? No, I didn't think so. In Rex I have a truncated value. So I don't think I need to move anything. Really strange. So we can try to actually debug that a little bit closer, but I need to save this line because I don't want to put it there oh my god, all the time. Right, so let me quit that. Break, start, run, layout assembly. All right, and let's just, you know what, let's actually go somewhere here. I'm gonna display this thing and also display this thing. Let's step into the floor. Boom. Can I also display Rex? I think I can. Cool. Okay, we're converting XMM0 to Rex, and we have minus 420. Cool. Step into the floor. Yes, yes. Oh shit, I could have actually just compared Rex. But anyway. Okay, well, I'm doing Pixor, it's 0, and then I'm doing this thing. So I would expect this thing to be greater or equal. So it should not skip, but it skipped anyway, because XMM0 was greater or equal than 0, which is not true. You know what? I'm gonna do the following thing. I'm gonna do the God Gamer move, right? So I'm gonna do CMP on Rax and 0. Maybe we can swap them, sure, but yeah. But I wanted to do God Coder move and just compare on Rax instead. But then I may lose information about the sign, so it would be better to do it like that. Okay, so let's try. I should probably not quit the GDB because I'm pretty sure you can restart everything. So break start, run layout, awesome. I only need this one, I think. Okay. Did I recompile? I keep recompiling it, it didn't work. Swapping these things didn't work, so it just doesn't care. So maybe we don't know something about Komi's Komi SD. It's very strange. Excuse me. Compare scalar ordered double precision floating points. Compares the double precision floating point in the lower quadrant of operand 1 and the operand 2 and sets ZF, PF, and CF flags in if flags register counted in the results. An order greater, so yeah. Operand 1 and operand 2 can be registered in the x86 location. The differs from UCOM SD instruction that is signals SMD floating point invalid operation. I don't think we need to signal anything, I don't know, whatever. So I don't quite understand. I even swapped them and it just don't work. Did you notice something? I didn't notice anything. It's zeros OF and SF. And they are used, it's not equivalent to CMP instruction. Oh, goddamn. Okay, can we just CMP on Rex then? Can we CMP on Rex? I don't think CMP on Rex is actually a good idea. Because we lose information about the sign, right? Because if you have -0.5, you're gonna have 0, and you don't know if you have to do that, if you have to do -1 or not. So, yeah. We still need to do comparison on this entire thing. Okay, example, show me example. Just show me example, I want to see example. Okay, so we have, then you can use any of JA, JB, GBE, above, below condition of their, okay, so, I think I need to use GB. I think I need to use a GB. Maybe, I'm not sure. We're about to find out. Break, start, run, and let's just lay out as in Stack Overflow. Yeah, I know. Imagine reading that. Okay, and then display Rex. Can I do it like that? Boom. Epic. A boom, and I'm gonna step into this thing. So we're converting Rex, XORing XMM1, comisd, comisd them, and if it's below 0, we shouldn't skip it. So I should have used above. I'm a very smart developer, yes. Should have used above then, because if XMM0 above 0, that means we have to skip the decrement. Alright, so break start. I'm speed running GDB. I'm speed running GDB. So I got a good RNG on the redrawing the screen, and there we go. So let me see. Cool. It's gonna be that. It's gonna be that. Like that. Oh. wait. Doesn't x86-69 just have a floor instruction? Look, we have like a shit ton of different instructions. Don't we have just a floor? 64 floor. How the floor double from... Yeah, is there an instruction to do that? Okay, so we can round. All right. Oh, it needs... Oh, God damn it. I'm sorry. Okay. All right. Back to the book. Okay. Chewbacca. It looks like a name of a x86-64 instruction, to be fair. Showing GB. Oh shit, did I forget to... God damn it. Never gonna succeed in the game industry. This is why I'm not in a Jai beta, by the way. Because I don't recompile my programs. Alright, so... break, start. Layout awesome. Run. Break, start. Run. Layout awesome. Hello, Rozoro. What's up? Okay, now. Decremented. Epic. Next one is gonna be this one, and then we jump into that one. We convert it into 420. We convert it into 420. We compare and everything, and we are about to skip the decrement, and that didn't actually decrement. We implemented floor. How about that? How about that? We implemented floor without SSE 4.1. Could you try minus 420? Okay, sure. It could be interesting, actually. All right, so that's a good point. We might actually switch the branching instruction. Okay, let me recompile like at least 5 times. I recompiled at least 5 times, and let's break and start. Right, and run layout ASM. Okay, so let's go back to here. SE. So it should actually decrement. Nice. Like the question is, why wouldn't it? It's like very huge negative number. Yeah, so I don't see any reason for it not to do that. So, all right, but thank you for suggesting that to check. And Yizu, kawaii. So we have a floor, right? We have a floor. I need to port print i64. I need to port print i64 because print i64 is a part of print f64. This is very important. It's part of it. So we also have a truncation, right? So this is like this. Oh, it's not really truncated. It's like a fraction, right? So we also need to implement this one. But this one should be pretty straightforward to implement if you ask me, because you take the value, you subtract the floor from it. Maybe we don't even need to implement anything here. Okay, let's port i64. So the problem with i64 from the natives that we use here is that it expects the stack, right? It expects the stack and we'll need to port it properly. What the fuck is this shit? What is... It looks like yet another like recent x86-64 instruction. Have you guys heard about this one? You know, speaking of new instructions. Yeah. Alright. So I'm gonna copy paste this entire stuff because it's very important. It's a part. Why is that above the segment text segment? Okay, let's put it here. Something from the fresh AVX. Yeah, that's what it is. Okay. So extracting info from the BM's stack. I don't think we need to do that. I think it's literally, yeah, we're moving it into racks, which means to actually port it to accept call convention. I just need to remove this thing. Yeah, I think that's it. So, and let me test that. Let me just test something. I'm gonna move racks 69420, and then I'm gonna call print i64, which is not really i64 because it doesn't work with negative values. So let's call it u64. Okay. So, and then I can just do the following. Oh shit, this one also adds a new line at the end of it. Oh, fuck. Alright. Let's just call it native. Yeah, it prints a 69420. That's cool. But I think it should do that without new line. So there should be a version without new line. So this should be something like. Okay, I think my tea is ready. I can't read through. This was an SMR stream. What are you talking about? All right. What's up? How's it going, everyone? Welcome back. I really want to pee. I want to call it something like print. So float has fractional part and it has a whole part, right? So we usually call it something that is not fractional, we call it whole, right? Because I don't quite remember. Can we just call it print whole? Yeah. I think this is how we call it. So print whole. And we need to get rid of the new line, adding the new line. No, let's not add the new line. Integer. Okay, so let's call it printing then. God damn it. Int. Print integer. I forgot the English. Yeah. So this is basically like a literal translation from Russian. That's why I think. That's why I suggested. Fractured by whole, butthole. Yes, fractured butthole. Okay. So we don't need to add a new line. Yeah, so it's one of those things like that Russians are struggling with. We wouldn't have separate words for these concepts. Right, so we use the same word to denote integer and whole. Right. You see what I mean? That's why it's really confusing for me sometimes. It's like, yeah. It's like we don't distinguish easy and simple. We use the single word for that. I keep bringing up this example. Yeah. From the Latin integer meaning whole. Yeah, exactly. So I mean, yeah. That's why in Russian language we use the same word for these two concepts. Right. So different languages basically evolve differently, right? Speak your Russian. Yes. Okay. So this compiles, and now it doesn't print any new line, and as you can see, it didn't print a new line, and that's exactly what we want to see, chat. That's exactly what we want to see. So we're gonna actually have oh shit. So I know that there is like FLD pi, which loads a pi into the stack. Is there something like that that loads a pi into XMM0? Do you prefer being bold? I personally don't care. But your mom prefers me being bold. Anyway, so no, there isn't. Okay, so that means I can do FLD pi and then move it into XMM0, right? So I search inspiration got smacked with leaves at this Russian spot. Nice. Why did you search for that? First of all, I mean, okay, I'm not gonna question that. All right. What's going to be the next thing we need to implement? We need to implement fraction, right? Print a frac. Print frac. It's going to be red. And what we're going to accept here, we're going to accept XMM. Right? We're going to accept XMM. XMM input must be less than 0. Right. So you have to make sure that it's less than 0. And then we're going to also implement printf64, which uses both of them. All right, so now we need to translate this thing somewhere here. So first of all, we need to print the dot, right? We need to print the dot, but to print anything in Linux, you need to provide the buffer, right? You need to provide some sort of a buffer. So let me put that buffer into BSS, and I'm gonna just call it, I don't know, X. It could be res B, so it's gonna be literally like a single byte buffer. So we're gonna just give it a pointer, give the kernel a pointer to this one single byte, and say that the size of the buffer is 1. So that's gonna be our approach. Right. So this is what we're gonna have, and I want to just print a single dot. And how can I do that? I'm gonna do that by doing something like X. It's gonna be single byte, and the dot is gonna be just this, right? Does BSS means bullshit segment? Yes, I think so. I don't remember what it stands for, though, to be fair. The only thing I remember about BSS naming is that it was some sort of legacy naming, I think. Why are you writing this in assembly? Why not? Why are you writing this in the chat? All right, so let's continue. So the next thing we need to do, we need to implement the write, we need to call the write syscall. So it's going to be rex, I initialize the write syscall, and then I'm going to be doing that in stdout. So if I remember correctly, RSI has to contain the beginning of the, so this is the beginning of the buffer, and the size of the buffer is going to be 1, and then we do syscall. Right, there we go. By the way, notice how like everywhere we print things, we actually print like single like characters. So this is where we're gonna do all of that. This is where we're gonna do all of that. So here is the dot. We're printing single dot. Dot of the fraction. Dot of the fraction. Okay, so now we also have M. We also have M, and we also have R, and we also have U. BRU, BRU. You know what's interesting is that, yeah, we only need to maintain these three variables, and we can allocate three different registers for that. So, which is gonna be cool. But we need to first pre-calculate this entire stuff. Oh shit, yeah. So this function, by the way, accepts two arguments. It accepts a single double and a single integer. Okay, so we're gonna have f fraction to print xmm0 like this, and then in rex we're gonna have n, which is precision. Right, so this is essentially the precision. And I already lost it, right? I already lost the precision. So, to be fair, maybe precision shouldn't be a parameter, runtime parameter. I think we can make it a compile time parameter. Right, it's going to be defined print frac n. And let's say that we're going to support like 10 digits after the period. Right, I think 10 is going to be enough. Yeah, so should be enough, because this is just a debug function anyway, right? We don't really care much about like anything else. Make it optional. Nice one. All right, so, and after that we need some sort of a counter. Oh, by the way, we don't even modify b. Might as well actually make it constant as well. In any case, so for the algorithm n is going to be xmm0, then r is going to be xmm1, and then wait a second. You can always just print frac p, which means accept precision. Yeah, sure. U xmm1. Does this make sense? Because this thing fits two double integers. How do you refer to like a different thing there? Or maybe, I don't know. Yeah, I think I'm gonna just use separate registers because it's gonna be easier for me. So for the m, I'm gonna start with 1. Right, we're gonna start with 1. And oh my god, I have so many magic constants here, and for all of them I'll have to have a memory. Okay, so let's do something like frac 1, and it's gonna be dq1. You can do two doubles in one exponential. Just use the p version instead of s version. Makes sense. But it's needed for parallel operations, right? It's needed for parallel operations, and this is not really what I'm trying to do here. But it could be useful in the future. Yeah. Okay, so for now I'm gonna use separate things, but maybe later I'm gonna do something else. Frac half dq05. We can also have frac 10. It's gonna be dq10. Do we have anything else? I don't think so. We also have 10th, which is gonna be this. So we need all of these constants. Can you see work with multiple floats at the same time? I think it can through the intrinsics. Yeah, I think it should be able to. But it's the code is gonna look worse than assembly. Yeah, by the way, can we like talk about how the intrinsics look worse and less readable than fucking assembly? Like holy shit. It's like, I'm supposed to be programming in a higher level language, what the fuck? Anyway. All right. So move XMM0. Thank you, Intel. Very cool. Yeah. Oh, wait a second. I have an epic idea, chat. Chat. I have an epic idea. Look. Do you like that? I think it's goddamn epic. So, and we move in frac 1. Frac 1. Cool. So here's the it's not house, it has to be SD. All right, so this is SD, and keyword. Your RAM means your mom. Yes, yes, exactly. It's the oldest your mama joke. By the way, we took that algorithm from a from a paper, scientific paper on printing floating points, and these are the naming from there. You don't actually need to write keyword. Yes, I know that I don't actually need to write it. The reason why I was writing it is because I wasn't sure. Like, I want the compiler to tell me if I'm just using registers incorrectly. Yeah. Because I don't want to make a mistake. So a little bit more type safe. Okay, so this is gonna be the frac, and I will have to keep multiplying this entire thing by 1. So I'm gonna keep the counter. Frac. What was that? Where's the define? Print frac n. There we go. So this is what we have here. By the way, can I undef things afterwards? So this compiles, and then can I just put things like that? Undef. Is that a thing? Oh shit, I can't. Trailing garbage after macro name ignored. You are trailing garbage. Oh, okay, so I see what it means. Thank you so much. Cool. Yeah, your mom. Cool. So after that, we need to perform n iterations. So I think I can do like test rex, and if it's equal to 0, I think I'm gonna be skipping all of that. So it's gonna be end, and there we go. And here's another loop in here. There we go. So here's the loop that we're doing. Frac end is okay. Call me trailing garbage. No. Okay, so how do I multiply? Let me guess. Mul SD. Holy shit, I know SSE. Alright. Yes. It actually reminds me of the Matrix scene. Like, I know SSE. Show me. Alright. So multiplies. So I suppose it just accepts the two registers, but he's beginning to believe. All right. Excuse me. We need an intermediate one. Intermediate one. Tax? No tax. Rex. Please, no taxes. No taxes in my x86 64, please. So it's gonna be frac. So let me open it somewhere here so I can see shit. Frac 10th. There we go. Frac 10th, and it has to be like this. Keyword. And then I want to do mul SD. No tax. Yeah. So and it's going to be n xmm3, and we keep multiplying this entire thing. Just keep multiplying it. And is it gonna? Oh, and after that, we have to decrement rex and jump unconditionally to loop. and then we're gonna check the condition yet again, and keep multiplying these things. Okay, looks good. Looks pretty good. I want to kind of test all of that. Texas, La Texas. Interesting. All right. Let's actually debug that and see if it's gonna work. So in here, to be fair, I want to remove this thing. 1/2/10th. And let's have pi, dq pi. Show me pi. So we're gonna put it here. So here's the pi. Can we do a little bit of Emacs magic, please? Align, regex, dq. There we go. Isn't that beautiful? I think it's goddamn fucking beautiful, mate. I kind of enjoy this recreational assembly programming. It's kind of cool, I'm not gonna lie. So there's a Frank 10th. Okay. So let's do GDB native test. Native test, we're gonna break at start, run layout asm. Okay. Oh, and I never actually utilized anything here. I'm an idiot. I'm a dummy. But first I need to actually find the fraction of this thing. So it's quite important, I think. So let me try the following thing. So I need to like take a fraction of that. Maybe I can have a separate function for it. So we have a floor, we have a print int, and what we can introduce here is frac. So the input and output for this one is also going to be through XMM0. So it's going to be input and it's going to be output. The thing it does, right, it gets a fraction of this thing. So this one, does it fit into there? Does it actually fit there? Okay, sure, why not? So that is that 10? Is that 10 of them? It's actually more than 10, but okay. Let me try one thing. So this is 10 actually. Let's have this. So now we have 12 characters, but the precision is 10, so it will let us test that properly, more or less, I think. So then we have a fraction and XMM. So to have a fraction, right, so what you have to do essentially, you have to do floor x, x minus floor x, right, x minus floor x. So what I'm thinking is that, can I push XMM0? Is that a thing you can do? Ah, yes. Love being slapped in the face. Memory? Memory? I guess it's memory time. I don't know. I mean, I can still put it in the stack. RSP, move DQU. Let me understand. I don't understand this thing yet. Move DQ. Move unaligned, interesting. From a source operand to the destination operand. Okay. I have an idea actually. Because the memory can be, the global memory can be actually used. Oh, yeah. Okay. I was about to came to the conclusion that I need to use a stack, but you suggested to use stack. Okay. But you have to like allocate enough memory on the stack first. So you have to subtract RSP8, which is the size of a single integer there, and then you can do move DQ XMM0. I mean, I think first it has to be like this, doesn't it? I think it's the other way around. Ah, 16. Well, yeah, that makes sense. So we have a little bit of waste, but that's totally okay. Okay, and then I can do add RSP16, so I should not forget to do that. Speaking of, by the way, this is a prime example of this thing. This is the prime example of the thing that I keep talking about. So people say that in C, all of the memory management is manual, right? So in C, you manage all memory manually, which is fucking wrong. There are automatic variables, right, in C. Let's actually go somewhere here. So this is like a prime example of this, what I keep talking about, right? So if you have a variable on the stack, you don't have to deallocate it. People don't know that even such a simple thing that everyone takes for granted, you have to work for it in assembly, right? In assembly, you allocate shit on the stack, and you have to not forget to deallocate shit on the stack, otherwise you won't be able to return from a function call. So no, you don't, like, not all of the memory management in C is manual. There is automatic memory management on the stack. People just forgot, they just take it for granted, right? So yeah. Imagine not knowing what auto keywords mean. I mean, it's a type inference, right? So everybody knows that. Anyway. Oh, also VLAs. Oh my god. By the way, in print int, we kind of use VLAs. Look, so here's RSP, and we iterate. So we have a loop, and we keep pushing a character onto RSP. So we keep pushing characters onto RSP, and then we use RSP as the beginning of the buffer for the write syscall. So technically, like, we're having some sort of VLA, for print int here. So, and this is something that you also have to do manually. So yeah, so as I'm iterating, I'm just keep stretching the stack byte by byte. All right. So yeah. What was that? Oh yeah. So I saved it on the stack. And afterwards, I want to call floor. Right. I'm calling floor, and now in XMM I have the integer part. I have this piece of code. Let's take a look at your piece of code. Show me your piece of code. Looks okay to me. Looks like a regular C. I don't know why. Classic C error handling. Yeah. So, and then you have like some sort of errors here, probably. Yeah. It's a classic C. What can I say? It is what it is, and it isn't what it isn't. But I do understand why would you hate it. So here's the call floor, and then I'm gonna be moving XMM1 to RSP, right? XMM1 to like from RSP to XMM1, right? And now I have a whole part there. I have the original value there and the integer value in XMM0, right? So, and after that, can I do something like, oh shit, okay. So, that means in XMM1, I can do sub SD XMM0, and after that, do I have to do it like that? Why do I need the stack actually? Because I need the original. Okay, one more time. Wait a second. I need to implement frac. So essentially, frac equal this, right? frac x floor x. Make sense? So I need to preserve original one. There's literally 16 XMM registers to use. But I don't know what register floor will use. And floor may change its implementation in the future. So you see what I mean? That's why I need stack. Okay, so do I need why do I need DQ? Why can't I use like SD here? Why does it have to be unaligned or something? Is it really important? Maybe it is important. I don't know. In any case, what I need to do, move after that, move SD, XMM0, XMM1. So, and now the result is going to be XMM, move dict, okay. If you use move SD, I think RSP needs to be 16 bytes aligned, or bad things may happen. Okay. So, yeah, but racks, we're not using racks or anything like that. But I think for moving like these two registers, I don't think it's important, right? I don't think it's important. It's only when you're interacting with the memory or something. All right. So here we have a frac. Here we have frac. And what I want to do, I want to move DQ, then XMM0, Q word pi. There we go. So we have a Q word pi. And then I'm going to call frac. So, and what I want to see, I want to only see this part here. So that should actually work, I think. That should actually work. A mismatch in the operands. Okay, that's cool. I think maybe for now I'm gonna go with this D because that thing apparently stores the whole thing. For now I'm gonna go like that. Okay, let's see if it's gonna work or not. Layout ASM. So do I have any of this stuff here? So all right, so next one. So we have the pi in here and I'm gonna step into the frac. Okay, so I'm allocating a little bit of memory on the stack, right? And I'm moving stuff into the stack. Okay, so then I call floor, and as you can see, 3 was successfully floored. Next, I'm recovering this original value. So as you can see, I recovered this original value. I'm subtracting that value. Well, there was a little bit of a loss of precision. And then I'm moving it back into XMM0 and I'm deallocating the stack and I return from all of that. There we go. So we basically got the fractional part of this thing. That's right. So now we have a frac, which is quite convenient, right? So and the reason why I wanted to have that is because after you did the frac, we can now try to call print frac, right? So because one of the premises of the print frac is that the value has to be less than 0, right? Less than 1, I'm sorry. I think I need to update some of these values here. Yeah, less than 1, excuse me. Has to be less than 1. Okay. Maybe we can now try to debug that and see how M is initialized. I think M should be initialized quite well. And by the way, I think for a little bit more convenient way of working with all of that, I want to store all of these things on the stack. Let's actually store them on the stack. I think it's going to be convenient for us to store them on the stack. Alrighty, but before we store all of that in the stack, I'm going to do break start, run, asm. Where's my template? I think I'm gonna also do like 2 in here just in case. What is ASM stands for? You're begging for a your mama joke? Because there's M in there. Okay, so this is what we do here. So we have pi, right? And then we take a fraction of your pi, and then we're stepping into the print frac. Right, so in the print frac, we're not doing anything particularly special. We're just printing a dot. And here is the dot that was printed. Okay, now I'm initializing this thing with 1, and Rex, I think I need a Rex as well. So let me also display Rex. So here's Rex. And we keep initializing this entire thing, so we'll have to go down to 10. We'll have to go down to 10. But what's interesting is that since n is a compile time value, it is a compile time value, do we really need to do all of that? That's a good question, right? You know what I mean? If it's a compile time value, can we just like calculate it at compile time? I think we should be able to. Print frac. So we print in the frac, and instead of move SDM to 1, oh yeah, you will have to store it first into the. I see. That's kind of painful. That's kind of painful. All right. So what I'm thinking is that, like, if you try to move, so we have 1, right, and it's a keyword, right, and you try to move a value that is like computation, so divided by, let's say, frac print frac n, right? Is that something that will work? Expression syntax error. I don't think this one is gonna work that easily. But if you try to do something like this, what the fuck is going on? Okay, it still doesn't work. Okay. So how can you put like like immediate? Why it keeps showing me this thing? All right, so it's probably not gonna easily work. So we'll probably have to compute it at runtime. So I have to go a little bit back. I'm a little bit tired, chat. Oh, yeah. It's too many things going on. Too many things, but it's really interesting. All right. So let's try to allocate all of that. So we're gonna do RSP sub RSP. Wait a second. Since I'm using SD, I don't have to do the 16 here, but I can do that just in case. I can do that just in case. So since I'm using SD, it doesn't really matter. So it's gonna be 8 multiplied by 3, and then we can have an offsets for this entire thing. So M is going to be 8, 8, oh my god, 8, I'm really tired, holy shit, 2, 8, 3. All right, so this is going to be offsets for this entire stuff. All right, and then we probably don't even need to do any of this stuff. So it's going to be add 5 tries to yeah, I'm tired, so not gonna lie, I'm really tired. So maybe I need to make a small break. What the hell is going on? Jiang, like I looked into GDB init, it didn't really work for my cases. It was really annoying to modify because I constantly need to change like slightly how my debugger works, and it's really annoying with GDB init. I know about GDB init. Thank you. Yeah. GDB by itself is just not really a convenient thing. Like, yeah. Because for different programs, like I use different languages and I need different configurations of the programs, and that means I have to constantly tweak this GDB init, and it's as annoying as doing that manually all the time. At least for me, like it's just, I tried that, it doesn't work. Yeah. It's in a local folder, I guess. Anyway, even within a single project, it also gets really annoying. Okay. I think I need to make a small break. Small break. 2 minutes. Right, so is it gonna be 2 minutes? It's gonna be 3 minutes. I think it's gonna be 3 minutes. Oh fuck! I forgot. I almost forgot to do one thing. All right, let's have a small break. You guys have fun. All right, welcome back. What we were doing, I don't remember. So here are the offsets. Here are the offsets, and interestingly enough, to facilitate all of that, so it's gonna be 1, 2, 3, and yeah. God damn it. All right. So, and essentially, yeah, so here we initialize this entire stuff is going to be XMM0, right? So we're initializing all that, and then we have to move RSP minus M, I think. Actually, yeah, do we need to, yeah, I think we need to do that. So it has to be like plus M in this particular case, right? So we're gonna start them like in a slightly different order. That makes sense. All right, and oh shit, I have a cool idea. By the way, I have a very cool idea. How about it's difficult to maintain. So I was thinking about, like, here is the size of this thing, and this one is going to be essentially R, like M plus 8, and this one is essentially R plus 8, but then I cannot easily change the order or anything like that. So yeah, but that would be actually kind of cool. And then you can even have like the size that you need to allocate, like as size, which is just U, and you can just use this size. Not sure how useful of a thing this is, right? So how useful it is, but in such a thing as assembly, it could be relatively. I feel like I'm gonna confuse myself, but maybe without that I can confuse myself even more. So yeah, this is RSP, this is size. All right. So we're allocating this thing. Oh, and that one is very interesting. Top of the stack. Yeah, that's true. 0, and that thing has to be then U plus 8, and this is essentially the size, right? U plus 8, and we also have to undef size. Cool. So it's almost like defining enumeration or something like that, right? If you know what I mean. So, and the problem with this approach is that it makes it difficult to reorder them. So, yeah. Okay. Look at the massive headache. Oh, you don't have to say anything. Don't worry about it. All right. Okay, we're loading XMM into that. We're preparing an XMM, and then once everything is prepared, we're taking RSP plus M and we're saving XMM there. So this is how we prepare this entire thing. There we go. Cool. Allocate stack variables. Might as well actually put it somewhere here to indicate all of that. And then we can do something like this. Deallocate stack variables. Deallocate stack variables. Initialize M to B. N minus 1. Well, I mean, it doesn't matter because it, yeah, we're still translating it. Okay, so after that, I'll have to do multiply M. Oh shit, M is a completely different thing now. So it has to be XMM0, and XMM3 could be XMM1 anyway, so it's intermediate stuff. And also we multiply this thing XMM0 with a half, with literally a half. And now, and then we're saving it back into the memory. So we're bringing it from the memory, calculate this thing and saving it back to the memory. All right, mismatch operands. Mismatch operands. I suppose we'll have to do something move SD XMM1 like this, and then XMM1 one more time, and that will work. Cool. All right. Initialize M. That's what we did. So this is the loop to initialize M. The next thing we need to do, we need to initialize B. We don't really have B, so it doesn't really need any of this shit. Okay, so the next step is going to be initializing R. Initialize R. And it's just literally the input. And did I fuck it up? I think I did. I think I fucked it up instantly, right? Because input is located in the XMM0, so we need to initialize it here. So I'm gonna be moving keyword RSP plus R XMM0. So we initialized R, and R is equal to the input. That's cool. Then we initializing M, and we initializing U. Initializing U should be pretty interesting. Initialize U. So initially is gonna be like this. So move SD. So XMM0 is already R. It is already R, which is kind of cool. Which means that I can just multiply move SD XMM1, and B is gonna be 10. So I put 10 here. Then I multiply this thing XMM0 but XMM1, and then I also call floor, so now in XMM I have a floor, and I move keyword RSPU XMM0. There we go. We initialized RUM. We initialized all of the three main variables in here. Three main variables in here. Cool. So that's very, very cool. So maybe I'm gonna actually put these things. Not sure how readable it becomes, but I just want to indicate the end of this section. So maybe it's gonna be readable. As you know, sometimes it's kind of difficult. So, and also I can paste this entire stuff. Initialize R, U, and M. Cool. And then delocate this entire thing. Nice. I want to kind of step through the debugger for this entire thing just to see if it's gonna work or not. Okay, so we have invalid opcodes because yeah, you have to do that from the memory. Yes. Let's go. Break start. Run layout awesome. Okay, so for temp first, did I? Oh my god, I closed my temporary buffer where I kept all the display things. Okay, so that means I have to look into them one more time. So here's this thing. So I forgot what we need here. Okay, so I loaded this entire thing. I think it has to be. Yeah, it already prints whatever I need here. So if I take a look at v2 double, right? So there it is. Here's v2 double. And then if I try to display this entire thing, okay, that's very cool. And I want to display as many of them as possible. All right, so, and let me also save that into the temporary buffer. Right, so it's going to be 0, 1, 2. Okay. So we're taking the fraction, right? We're taking the fraction, as you can see. Now we have a fraction in x0. Let's step into this shite. Okay, so that's very interesting. We're just printing the dot. Here the dot has been printed successfully. Okay, I allocated shed on the stack, right? So this allocated shed on the stack. Can I now take this entire thing? RSP. If I take a look at the RSP, so it's a void star. Can I now reinterpret it as a double star and then dereference this entire thing and also display 3 of them? Can I do something like that? I think I should be able to do something like that. Right, you see? So here is RSP, the beginning of RSP, and here are these things. That's pretty interesting. And now if I try to do a display, now I can see shit on the stack. Isn't that amazing? I think it's goddamn amazing. So I also wish I could see some comments here, but I don't think it's going to be useful. All right, so we're moving pi onto the stack. Actually, not pi, but input. Here is the input on the stack. I think the next thing is going to be initializing u. We're taking the floor, and we're moving some of the stuff on the stack. I think now we're calculating the. Yeah, you see, we're calculating the another thing. We're calculating the another thing. I think it's not gonna stop until it reaches the 10, and once it reaches the 10, we're saving it. We're also multiplying by 5, and then we're gonna save that thing here as well. All right. So, and yeah, there we go. We initialized all of them, I suppose. We initialized all of them. Which is kind of strange. Yeah, I really like that I can like observe the stack like that. That's actually super convenient. Just literally see all of them. R is just that. U. U is this thing. It feels like I forgot to do something. That's what it feels like. Then I save it to M. So in M we should have that. In R, so what is R initially? What is R initially? Initially R is just the input, and U is that floor, so it's actually 1. So yeah, that makes sense. So the input looks correct. The input looks more or less correct. So after that, we need to perform all of these things, right? So we need to perform all of these things. Should be pretty straightforward, I'm not gonna lie. Right. So we just need to do this thing. Ooh. That's a pretty interesting program. Okay, so after this initialization, I'm gonna just put this thing here. So we're gonna start with this one. I'm gonna be moving this thing into XMM0, right? And then I need to multiply this thing by 10. So B is actually 10. And then I need to store it back into the memory. So it's going to be move SD RSP plus R XMM0. And keyword Keyword. Okay, I think that should work. And an invalid combination. Nice. Yep. Mismatch operand size. Yikes. Oh, I see. So I'll have to do that like this. Yeah. Cool. Nice. So this is what we have here. So we load these two things, we multiply one by another, and we save it back into R. Cool. Okay, so we bring this entire stuff yet again, XMM0, keyword, RSP R. I'm bringing it back yet again. Then I call the floor. And now I need to subtract it. But to subtract it, I need to move XMM0 to XMM1. Right, I'm moving it there. Right, then I need to load it one more time. Right. To be fair, maybe this is not how I have to do that. I can load this one into 1 then, right? So XMM0 has the floor, and XMM1 now has the full one. So I can do a sub SD XMM1 XMM0, XMM1 XMM0, and then I can save all of that from keyword XMM1. I think this is how we can do that. We're loading this in XMM, call floor on it. Then I load XMM1, subtract XMM0, which is the floor of that thing, and I store XMM1 back into the original place where it was. Okay, that looks cool. I'm a little curious, this headache is on a different side of the head than usual. Oh, okay, that's a little bit scary. I hope you get well soon, Django. Alright, so I need to bring M now. So this is going to be M, and what I need to do now, I need to multiply. I need to move SDXMM1 keyword 10, because B is equal to 10 if I remember correctly. Yeah, it is equal to 10, and it's not really changing that often. X equal to 10, and I'm multiplying XMM0 to XMM1, and I'm storing this entire stuff back into M. There we go. I think I implemented everything here, so this is the whole thing that needed to be implemented. That looks okay. So does it even compile? It seems to be compiling. Nice. So, and now we're ready to organize this loop. We need to organize this loop. Are you ready to organize this loop? So what's interesting is that we have this part repeating, so it should be pretty straightforward. So we can literally copy paste it there. But apart from that, oh, to be fair, in the original thing, in the original paper, what they were trying to do, they actually had post condition. They actually literally had a post condition, and maybe we can just use the post condition one to simplify the stuff. Yeah. So let me take a look at the paper. So here's the PDF, and I'm gonna do new PDF. This is not what I want. Okay, so so where's the algorithm? Yeah, this is what they had. This is what they had, and this is how we interpreted it. Alright, so what's funny is here. So maybe we need to... Oh, this is actually a frac. This is actually a frac. And maybe... Yeah, so this pattern is essentially multiplying it by p and then doing frac on it. So I think I can squash that into a single thing in assembly. I'm pretty sure I can try to do that. Well, at least this one could be rewritten as the combination of this thing. The combination of this thing could be rewritten as that. As just r multiplied by 10 floor frac. That's it. That's basically what it is. This is just single thing this, I think. You multiply it by 10 and then you subtract floor. That means you're taking only the fraction of it. Alright, so which means that to implement this entire stuff I need to do move SD XMM 0 Q word RSP plus R. That brings me this thing, and then I'm going to move XMM 1 Q word 10, so that brings me another thing, and then I do multiply SD XMM 0 XMM 1, and then I can call frac, and that gives me the thing that I wanted. So there's a frac. Here we go. Cool. So, and that entire thing replaces these two things, right? Because that's essentially what it does. Cool. If statements are a sign of a failed OOP. Wait, where is my... Okay. Let me see. I think we have ifs somewhere here. New if... Or maybe something condition. But there were actually, basically in this library, we had like if as an object. Which basically acts like it's then branch or else branch, depending on the condition. Yeah, so there was something like that. I think it was somewhere in here. Whatever. Oh, it was elegant object. Whatever. We're doing assembly right now. Okay, so we need to start doing the thing. Can you rewrite this in a post condition, by the way? Not OOP enough. Yeah. Okay, I need to do some experiments. I want to introduce frac in here. So this is going to be frac. And essentially, oh my god, return x minus floor. So this is what we do here for a frac. So, and essentially, when I do something like this, what I'm doing is r multiplied by b frac, and I can just remove that, and I can replace this entire thing with that as well. Cool. So now what I want to try to do, I'm going to try to do GCC, and then I'm going to try to run it, and it does work. It does in fact work. Nice. So if I add more things here, will it work? It does still work. So, cool. So the reason why I'm doing all of that is because I'm hoping to rewrite this in a post condition like this. So this one is true. If this condition not true, we're gonna break, and we're kind of moving this entire thing here. And it's really strange. Something is going on with the neighbors. They're just talking very loudly or something. Maybe watching something. Okay, so what I want to do here essentially is, since we had this entire stuff, so I really like this thing because, how to say that? It's very like, it's very assembly friendly. You can like literally translate it easily to assembly. And yeah, I think I've fucked it up at some point. So that's why I'm trying to rewrite it like that. So I think I'll have to do that. I'm feeling like it's gonna be worth spending time. We're not doing loop unrolling actually, by the way. You're just repeating a random word that you heard on the internet. Okay. So we're preparing M. So R is initially that, and U is initially that. So we're not doing any of this stuff. Okay. So and U is going to be equal to floor R multiplied by 10. Then R is going to be frac R multiplied by 10. So this is essentially what we're doing. And M is going to be M multiplied by 10. So that's what we're doing. If this is not true, we keep doing this entire thing, and I'm gonna do this thing. Okay, I'm gonna do compile, and it doesn't compile because we don't have true. Cool, still works. So this is a little bit more assembly friendly version, I think. I think it's a bit more assembly friendly version. So this is a digit, by the way. This is a digit. So I'm just a little bit afraid how we're gonna even calculate this entire stuff. It's probably gonna be a pain in the ass. Yeah. But overall, it still works. It still works. So let's actually go back and try to translate that. Let's try to translate that. So initialization. So initializing R. So first we need to initialize R, and we're initializing it to F, right? So then we are initializing M, and it's okay, cool. And then we're trying to initialize U, but it doesn't really need to be initialized, I think. I think it doesn't matter. So we can omit initialization, and some of this stuff can be omitted as well. So yeah, I want to double check that it still works. Yeah. Okay, so this is the whole thing. Everything seems to be working okay. So now I'm going to do loop. Right, GMP loop. Here is our loop. Within that loop, we should start doing this entire stuff, right? So let's start doing this thing. Okay, cool. So we need to load R. So move SD XMM0 is going to be RSP plus R is going to be keyword. For that one is going to be 10. Then we just multiply them together. Right, we multiply them together, and I store everything back actually into U. That's what's interesting. I'm storing it into U. There we go. So we solved that one. This one is going to be the following. It's going to be actually pretty straightforward as well. Okay, so multiplication, I forgot another one. Call floor. Yeah. So we multiply that and we call floor in it. Surprisingly enough, this one is similar, right? It's just we call frac instead. We call frac instead. And we save it back into R, though. We save it back into R. So this is the difference here. So in here, I'm loading pretty much the same thing. But M and saving it back to... okay, I forgot to multiply them together. And saving it back to M. I think I didn't fuck it up, hopefully. So yeah, we do that. So R10 multiply floor save to U. R10 multiply frac save to R. M10 multiply save to M. Cool. That's pretty straightforward. I'm actually not compiling the right thing. So what I'm supposed to, yeah, it's not build natives, it was... I had a script. Oh, it was build natives, okay. Can't find valid values for all labels. Possible recursive what? Excuse me? Oh shit, okay. Loop 1, whatever. Alright. So we translated that thing. So now we need to check this condition actually. Loop 1 end. So we'll definitely need this thing. Okay. So that's pretty interesting. We can check this condition first. So we can basically do a De Morgan law, right? So it's gonna be this or this, you see? And then we, when we do this thing, it's gonna be opposite. And then we do this thing, it's gonna be that. Right, so this is gonna be what we want here, and it does still work. So I think it's gonna be a little bit better to work with. So if R less than M, or this thing is greater than R, we'll have to quit. So what's interesting is that essentially, I think we can split this entire stuff into separate conditions, like that, right? Okay, cool. So, and that makes it even easier to translate to assembly. See what I mean? So this is literally assembly. What are you guys talking about? Talking about something interesting. Alright. Oil emerging cooling. Oh, okay. Interesting. So, move SD XMM0. So it's gonna be R. And another one we need to load is M. Okay, so we just need to compare these two things. R less than M. How can we compare them? So in Floor, we already know how to compare things. Right, so it's essentially com is D. All right. Oh, and by the way, this is really risky. Okay, and we want to jump if we are below, right? GB, jump into loop 1 end. There we go. So this is the first one, the first condition. All right, so that's kind of cool. That's very interesting because, like, it has to be exactly equal. Ah, okay, so it has to be between these values. That's why it works like that. All right. So if I try to compile, actually I'm not compiling the right thing. All right, it seems to be working. Now I need to prepare this value. So I'll have to do move xmm0 keyword 1 and then move xmm1 keyword rspm. So that's what we're doing here, rspm. And I'm subtracting xmm0 from xmm1. There we go. I get 1 minus m, and I'm gonna be moving xmm. So I'm moving it into xmm1, right? I'm moving it into xmm1 because then I'm gonna move xmm0 keyword rspr. So in xmm0 now I have r, and in xmm1 I have 1 minus m, hopefully. Yes. And then I can do this comparison, Comic Sans comparisons. Yeah, Comic Sans comparison, nice. And if it's above, we're better now. Okay, cool. Next thing, we need to print this shite. So this one is going to be very interesting. By the way, y is supposed to be between 0 and 10. 0 and 1 actually. 0 and 9. Yep. Cool. So we need to truncate it or something. Yeah, this is what we need to do. Okay, so first I'm loading y, pre-calculated y. So I'm loading pre-calculated y into 0. So it's gonna be like this. So we have y, and then we are converting it to rex, right? And then I'm gonna add 0 to that rex, and then I just need to print it. But to print this entire thing, I need to move it into x, I suppose. So I'm gonna move x, a single byte, by the way. AL. We might as well actually do AL thingy. It's gonna be AL. And then we're gonna do a write syscall. Where is the write syscall? So here it is. There we go. So here is the write syscall. There we go. So we take in U. We turn to rex, we add AL there, and then we take it, move it to the byte, and then we prepare everything here and perform the syscall. We're calling our sister syscall. Yes, that's what it stands for. Haha, I know. All right, so the ya instruction. Alright, so now we need to do this shit. So to be fair, this shit is relatively easy to do, I think. Because you only just need to add y. Yeah, let me actually rewrite it slightly. If r... Oh my god, sorry, man, thank you so much. You didn't have to, but thank you. Yeah. Thank you so much for 300 bits. Thank you, thank you, thank you. Yeah. I'm really sorry that sometimes I'm really grumpy and irritated. I'm trying to work on that. But yeah, thank you so much. All right. What I want to do. So if it's that, if it's actually greater, right? If it's actually greater, what we want to probably do is we want to add 1 to this entire thing, right? We want to add 1. And after that, we should be able to do this thing. Yeah. See what I mean? So this this thing is equivalent to this one, but this one is easier to translate to assembly. I'm really starting to think like an assembly, to be fair. Yeah. Oh my god. That Shadows, thank you. Thank you so much for 100 bits. Columbetko also, thank you so much for 300 bits. Really appreciate it. Thank you, thank you, thank you. To be fair, Columbetko also contributed a lot to the channel in terms of different contributions to the projects, and I also really value that. So yeah, thank you so much for all of the contributions. Because as I already said, like if you contribute, you know, something to the projects that gets merged, right, you essentially save me a little bit of time, and time is money, right? So yeah, thank you so much. So this thing is that, so I'm incrementing that, and then I'm just printing it. Okay, let me try to see if it does work. Look at that, it does work. And if I try to remove that, it yeah, it's like that. So it's a little bit easier to convert to assembly, in my opinion. So let me see how we can do all of that. Yok Rusty, I hope I pronounced it correctly. Thank you so much for tier 1 subscription. Thank you. And welcome to our assembly club. We're almost finished, by the way. I almost finished implementing the print frac. And once we have a print frac, we will be able to implement print F64. So we'll be able to print floating point numbers without using libc. So this is pretty much the idea here. This is pretty much the idea here. Excuse me? What the hell's going on? Navy Time Bomb, thank you as well for tier 1 subscription. Thank you and welcome. First subscription, by the way. So many first subscriptions. Thank you so much. I don't know. I've been a little bit grumpy at the beginning of the stream, and I feel like, I don't know, I feel a little bit bad about that. Hype Train, is that because of Hype Train? I think I actually disabled Hype Train. I was actually subbed with another account before. Did they ban you? Okay, I don't think so. But yeah. Alright, so we can try to do this thing. Poke Train, yeah. So, oh my god, this is not what I wanted. So yeah, by the way, I double check. It does compile. Cool. Ban evasion. Ban invasion. Okay, so I want to load up the U. Pug U. And here we're gonna be loading up the one and only. And then we're gonna be incrementing. So it's gonna be add. To fair throughout the whole thing here. We're only subtracting, and yeah, so it's gonna be add 1. XMM1, and we need to store all of that back. XMM0. I'm here only for a couple of streams ago, and I think you're the best science and really? I don't know. Thank you so much. I really appreciate the kind words. Alright. So what's interesting is that we can load Y in here, and then we can, yeah. then we need to print all of that. And to print all of that, we already know how to print all of that, actually. We already have this thing here, so we can just repeat it here. Alright. So, let's load up R. Do we have a half? Yes, we do have a half. And for the 1, we're gonna load up a half. And then I'll need to do a Comic Sans comparison. Here we go, Comic Sans comparison. And if it's above, right, if it's actually above, we have to perform this thing. We really have to perform this thing, but that means I'll have to invert this. Okay. Skip inc. So this is what we're doing here. We skip increment. Increment. Right. So yeah. So what other instructions do we have? GA, GB, and what's the other one? GB condition is met. GA equal. So I suppose that's what we need here. So because yeah, gbait. Yeah. If this thing is false, we want to skip the entire stuff. So that means it has to be below or equal. Below or equal, that's what it needs to be. If it's true, we'll have to do that. And this is how we yeah, this is how we do that. Yeah. So that's the whole condition here. And then we print the fraction. Alrighty. So I need to compile some stuff here, build natives, and it does compile. Okay, the print frac is officially implemented. It's huge. Holy fuck, it's huge. So the size of this thing is how many lines? 121 lines of assembly to print floating points. We're printing floating points from assembly without using libc. Let whoever understands that, whoever understands what I just said, let that sink in. We're printing floating points in assembly without third-party dependencies, without libc. We only depend on the Linux syscalls. We're almost done. We're almost done. We're implementing this algorithm here, actually. So that was never done before by me. So I was always scared about doing that, but now I can do that. And to be fair, I'm a little bit afraid to admit that, but I don't understand algorithms. So I just literally copied it, but I implemented it in C. I know that it works. So I know that algorithm works. Anyways, so what I'm doing here, I'm taking the pi number and I'm taking the fraction of it, and then I'm printing the fraction. So the difficulty here is that we only have a description of an algorithm that can only print fractions. Only prints fractions. So we have two separate algorithms. We have an algorithm that prints integer part and then fraction. Is beginning to believe, okay. All right, so everything seems to be compiling. So let's go to the debugger. Debugger. Native test. I'm gonna break on the start and I'm gonna run this thing, layout, assembly, boom, boom, boom. So temp, I want all of these things here. Cool. So we loaded pi into this thing and we take the fraction of that pi. Here is the fraction of that pi. So we're about to print the frac. Okay, so let's take a look at what's going on. This is completely unreadable, by the way, but we can try to see what's going to happen. Oh, I also wanted to see the stack, and I didn't save the printing of the stack. Okay, so the stack has to be somewhere here, so it's going to be RSP. So here's RSP. I'm converting it to a pointer to a double, and then I'm dereferencing the double, and I'm taking 3 elements from there. So here they are, and I want to display all of them. Right, there we go. So here's what we have on this stack. The stack is a little bit dirty, but that's intentional. right? So the stack is a little bit dirty. Really apologize for my dirty stack. All right, so we're initializing some of the things, and oh yeah, we're initializing this thing here, which is basically a very small number, the precision number actually. It's a precision number, how much of a precision we want to have. All right, and then we proceed with the rest of the stuff. What I'm trying to do is just see what's gonna happen. Okay, so it's doing things, at least. I think it's doing things. Okay. All right, so let's quit this entire stuff. And try to run this program. Look at that. Isn't that amazing? Let's compare this stuff to what we've got in the fucking memory, mate. Did I just first try this, mother flipper? Did I just first try it? 1, 4, 92, 65, 36, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, precision 10. It not only printed 10, it also rounded up correctly, right? Because you have 8 here, so it rounded it up into the 6. It worked, actually. But that's only the fractional part, right? It's only the fractional part. So now we need to implement the proper print F64, right? So essentially what it does, it first truncates the thing and uses print int, right? It uses print int, and then it uses print frac. Let's quickly do that. So, okay, the input is going to be actually in XMM0, right? So the input is in XMM0. We also need to do the conversion, right? So XMM0. There we go. So here's the conversion. So we have the integer part, and we call print integer. So I suppose print integer doesn't touch XMM0, so it's not supposed to be doing that, but it would be better to save it anyway. So call print int, so we're calling it there. Okay, cool. Then in XMM0 we still have this thing, so we're going to be calling call frac to convert XMM0 to frac, and then we're going to call print frac. But that's not enough actually, because we also need to print a new line afterwards. So what we're going to be doing is we're going to be taking x byte, and we're going to save in a new line there. So we're saving it there. It's probably not going to work. We may try to recompile that, and it does compile. Okay, so it's going to work. Cool, cool, cool. So and then I'm going to do a syscall. I'm going to call write syscall to write that last byte. And that should be it. So we're truncating everything, printing the integer part, then we take the fraction, we printed the fractional part, and then we print in the next last new line. Okay, so the next thing. We're loading pi into the XMM0, and we're just calling print F64, and that should fucking work. Okay. Tech 256, hello! So you won't believe what the fuck we're doing here, actually. Something is different, yeah. I actually lost some weight, believe it or not. Which is not a joke, I lost some weight recently. So yeah, including hair. So hair also weighted a lot. So, what we're doing? Tech 256, we're doing very cool thing. We're printing IEEE 754 numbers using assembly without using libc or any other libraries. We don't depend on anything except Linux syscalls. It's not a joke. We literally don't depend on anything. We implemented the algorithm, specifically we implemented the fixed point fractional output algorithm in assembly. So, and I think it works. We're on the latest stages of actually checking it out. So, and yeah, we don't depend on anything. This is actually super fucking cool. All right, so what we have here in the memory, we just provide the pi, and we're trying to print pi up to the 10 digits after the period. So look at that. Here's the pi. Here's the pi. So I don't think it works on. Let me see. Random shit. Let's put some random shit here. It's gonna be something like this and something like this. So absolutely random number, right? So we're gonna put a random shit here, and we're gonna try to print this random shit, and let's see what's gonna happen. Boom. Here's your random shit that got printed, and let's compare it to the original random shit. Okay. Okay, so it's pretty close. All right. So this is because I see what's gonna happen. What's happened here? Yeah. So you have 9 characters here. So it basically assumed that there is an error at the last character. It's actually pretty close. It's actually pretty close because the precision here is 10. The precision is fixed, by the way. So that's the sort of like premise of this algorithm. It doesn't know the precision. You have to tell it the precision, and it will print a floating point with that specific precision. Have you fixed for minus 420? I think I fixed it. I think there was no error. I think it was actually decrementing it correctly. Yeah, I think. But yeah, so overall this entire thing works. And that is pretty goddamn cool, and I'm super proud of it actually. So we can take a look at the floor one more time. As a matter of fact, we can actually check it ourselves. So minus 420, right? So I'm actually moving random shit. Then I'm gonna do a floor, and then we're gonna print the result of the floor. So now we don't even have to rely on the debugger. All right. Oh shit. It doesn't support negative, though. I think it's gonna break. I forgot that we don't support negative, but yeah. Yikes. But we can do that in the debugger. So yeah, we can do that in the debugger. Okay, it's gonna be GDB break start, and okay, I'm gonna just put this thing here, and there we go. Run layout asm. What do we got? Okay. So here we have minus 420, and we're gonna call floor, and it worked. Oh shit, I see what you mean. Yes. God damn it, I'm an idiot. I see what you mean. I'm a little bit tired. Yeah. I'm sorry. Sorry. Alright, so we are... It worked. God damn it. Get me some slack. I actually implemented quite cool thing here. I implemented like a floating point printing from scratch in assembly. So I think it's something. Yeah, Jai. Yeah. Okay. I'm gonna recompile it 5 times, just in case, and let's just try to do that. Wait. Template. Break. Start. Okay, did it work? Oh shit, it didn't. Layout asm. Yeah, there we go. Oh shit, it didn't work. Did I not recompile? Okay, wait. Oh, I see what you mean here. I see. It's a completely different logic. It's not about equals or something. It's a completely different logic. You need to compare fractional part, and fraction depends on the floor. I think I don't have a Okay. I didn't have an energy to fix all of that. Okay, I'm gonna put to do like this. So floor minus 420 is equal to floor to actually minus 421. So this is a bug. Okay. Nah, it's okay. We still won. We still won. It's a partial implementation. Since we don't support negative numbers anyway, so it doesn't really matter. Okay, and printf to do printf 64 does not support negative numbers. So this is something that we can implement a little bit later. So that's cool. That's very, very cool. I think it could be actually a separate project somewhere. Yeah. So let's actually move all of that stuff to like separate thing, because then we can reuse it in the main program. Okay, but yeah, so the main premise here was that you can take pi and just print the pi, and we're gonna do native test. Cool, it does work. Did we put stolen? Yeah, we didn't put stolen. src print f64 stolen. Oh shit, I forgot where was the original link. Okay, so can I, how to print floating point numbers awkwardly. Okay, how to print floating, yeah, here it is, I think. Did I close it? Okay, I didn't close it. So this is ASM. That Shadow X. Thank you so much for.
Широко улыбается.
Thank you so much for tier 1 subscription, for 5 months of tier 1 subscription, and welcome to our Epic Assembly Club. Did you just subscribe like 20 minutes ago? I think they actually sent beats or something. Yeah. Yeah, that was bits. All right. So let me see. So how are we gonna call this project? Print. I'm gonna call it print f64. Yeah, this is literally how I'm gonna call it. And I'm gonna copy this entire thing here, and this is gonna be literally called print f64. All right. So, and I'm gonna add like a build sh. The shared thing just popped up. Oh, interesting. So build natives. So this is what we're trying to do here. Set xe, and I'm gonna name it to print f64. And I'm gonna git ignore print f64, and also any all files. There we go. Also do that, and if I try to build this entire stuff, it gives me that. All right, so let's do readme. Print f64 implementation purely in assembly without using any third-party dependencies, including libc, libm, etc. We are only depending on Linux syscalls. I can even list the syscalls. Linux syscalls. Syswrite, and sysexit. So this is literally two syscalls that we use here, exit and write. Okay, so quick start. Dependencies. Well, we just said that there's no third-party dependencies, but I mean, build dependencies. Okay, so NASM. So NASM US. So this is like the major ones, and then we're gonna do console build sh, and then print f64. Right, and that's pretty much it. Also, I want to put the reference here, references. So, and in the references, so we're actually kind of like referring to a scientific paper, and I think that you actually reference them in a particular style. Does anyone know how to reference like white paper? I've never done that before. I'm not a scientist, but I knew that you, yeah, how to cite. It's citing. Yes, you can find it in Google Scholar. Okay, Google Scholar. Okay. Banned? Well, I'm behind VPN actually. What the fuck? Okay, can anyone actually go to the Google Scholar and give me the... I'm banned and... Oh, wait a second. Hello? Oh, alright. Name of the article. How to print floating points accurately. Wait a second. How to print floating points. Floating... Yeah, this one. Yeah. Imagine literally being banned on Google. Holy shit. Yeah, like bibliography, I guess you can look up examples. I mean, you can grab them on Google Scholar. So you just need to know the name of the article. Because I want to feel like a real scientist. I want to feel like a real scientist and stuff like that. Thank you so much. I'm gonna believe Igoduke because he's trusted. So yeah, there we go. Proceeding of SCM. Yeah, it was good. Thank you so much. How to print floating point numbers. Now I feel like a real scientist. Holy shit. Isn't that amazing? I think it's goddamn fucking amazing. Favoritisms, right? Well, I mean, yeah, Igoduke like a longer viewer, first of all. Second of all, he's also trusted, and he also a sub. Like, why wouldn't I favorite Igoduke? Like, what's the reason to not do that? Sorry, it's just, it is what it is. It's the internet. Alright. So, yeah, that's pretty cool. I'm doing a similar thing for my diploma, but the style... Oh, yeah. The style has to be different, I see. So in Russia, we have different standards and stuff like that. Okay. Let me take a look. Upper citation. Scientific journal. Okay. That's pretty cool. Let me take a look at this thing. Thank you so much. I think Google just doesn't like me. Title or DOI? Okay, let's try to search it by a title. We'll be able to find. Maybe that's, yeah. Cool. So is that how we can cite it? Yeah, I guess that's how we can cite that, but I remember that on Google Scholar it just gives you like example that you can copy paste, specifically generated for you to copy paste. Oh, site, okay. Site source. Do I have to? Okay, I clicked on it. Website. Okay. Oh my god. Oh my god, I'm an idiot. I'm alright. Web page or article. Okay, so can we just do it like that? Don't know. I'm too stupid for this thing. I'm sorry. All right. So let's do a committee. I'm also not really motivated to figure out how to use this website because I already got what I needed. So that's why I just don't really care that much, because there we go, I have it. So, and the only thing I want to do, I want to just commit this entire thing. That's why I'm so stupid. And I'm also was streaming for 5 hours. Chat, give me some slack. Like, cut me some slack. Seriously, come on. You choose website, but you use journal article. Okay, I'm gonna do that next time. Thank you so much. All right, so ready, set, go. All right, so let's push that. You see, I'm not a scientist. I'm also tired. I'm running out of excuses. Chat, stop! I'm running out of excuses. All right. Okay. Print 64. Okay. So this is not what I wanted, and there we go. It's going to be public. So we're going to release it under MIT, I suppose. Boom! Look at that legitness. Release under MIT. All right. So let me grab this thing here. Add origin. Boom. Yes. So yeah, that's the result of today's stream. It's pretty cool. "227 lines of assembly, and I think I learned how to work with floating point numbers in assembly quite extensively. I mean, I implemented like the entire printer of this thing. So that's pretty cool. Assembly is actually quite cool for recreational programming, I think. So yeah, so you can find this thing here. Yeah. And I guess it is time for me to go. It's time for me to go. Thanks everyone who's watching right now. I really appreciate it. I'm sorry that sometimes I get irritated and grumpy and all of that stuff. I don't know. So, there's no really reason for that. It's just over the time things, you know, accumulate. Anyway. Thanks everyone for all the subscriptions, donations and stuff like that. Thank you for supporting what I do. Really, really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow, according to the schedule, we're gonna be doing Advent of Code in Haskell. Yes, we do continue this series. Even if nobody's gonna watch that, I still wanna continue that challenge, finish that challenge. So I think we already solved 6 days. Right, so tomorrow hopefully I'm gonna solve like 7, 8 and 9, we'll see. Since the problem probably gonna become more difficult, it will take more time for me to solve them, especially in Haskell. We'll see how it goes. So, and also check out our schedule page for more information on different projects we're working on. Thank you, that Shadow X, thank you so much for 100 bits. check out the schedule page, right? And also check out our VODs channel where we upload all of our stream recordings. This stream is going to be there, but tomorrow we upload them on the next day. And also check out our Discord server for offline discussion with the community. We have a pretty cozy community built there. And while you're waiting for an epic advent of code stuff, how about we rate somebody? We haven't rated anybody for quite some time. So Yesu Kawaii desu, of course. Only caught the end. No, it was actually pretty cool. So we implemented IEEE 754 printer in assembly, purely in assembly, without using any third-party dependencies like libc or libm or anything like that. I think we have a Sodin Weeby mod. Yeah, we have a Sodin Weeby mod, by the way. It's not even IAI, it's literally called Sodin Weeb. So who should we raid? So we have quite a few people to raid. So we raided them recently, we're raiding them recently. So who else can we raid? Do you guys have any suggestions? Alright. Togglebit. Is he streaming right now? Probably. I think we're raiding them. I guess we can raid Togglebit. Sounds good to me. Since he's probably doing like Rust, so which is very close to what we're doing. Okay. A raid, not Ursai. So yeah, we're about to raid a Rust stream. How about that? Togglebit. Alright, boys and girls, get ready for the raid. Get ready for the raid. And I see you all tomorrow. I love you all. Mwah. Mwah.